we can go ahead. So what we'll try to do today is cover the final part of the inelastic behavior, which is typically related to fracture. So the fracture is a very important phenomenon that is studied for many engineering problems. And you really try to avoid the risk of the fracture. The historical developments start with the linear fracture mechanics, which is, as I said, simplified theory for studying the fracture, where you actually assume a certain crack, and you then consider whether this crack is going to propagate or not. The problem arises when you have to define when the crack is going to start, because the crack could be considered only like a final stage of a, let's say, the inelastic behavior phenomena. For example, with plasticity, you would have these dislocation type of activities where the shear stress reaches the limit of elasticity. Then you have start this micro sliding at the level of dislocation, typically at the level of microns. And then these dislocation have a coalescence, they kind of merge into one, and you have something called yield lines. So there was really also development of a very simplified theory where they study directly yield lines and the stability of the material and the yield lines. In the damage mechanics, you are considering damage to be representative, this damage variable to be represented by microcracks. And again, these microcracks can get merging together, or we call coalescence. And then at the end, you get a macrocrack, and then typically the macrocrack starts with the so-called softening behavior of material. When you go above the peak of resistance, and you go down irreversibly, basically by increasing the strain with the stress which is decreasing, until basically you reduce stress to zero, because you simply tear apart your solid body or your structure. So all these phenomena have to be studied, because for many industrial application, we do care about fracture. I already cited last time this kind of now sadly famous accident of a Boeing 737 MAX with basically part of the airplane with the door tearing apart, and luckily managed to land. So the main difficulty of studying these type of things is both in terms of experiments and in terms of numerics. First of all, in terms of experiments, it is really very hard to control the failure process. So when you look into this typical stress strain diagram, you can go until a certain level, and then even the best type of experimental operators, they cannot control the structure, the specimen, to go very slowly down, because the softening is very violent type of phenomena. It's actually related to instability. You can actually lose stability of your structure, so controlling stability or preventing instability is certainly a very big challenge. In numerics, this is related to something called localization, because if you have a very large deformation, when they go to the softening phase, they also have tendency to concentrate. So you have to handle very large displacement gradients leading to very large deformation. And so typical finite element development are not meant for such a large, so you can have at the end obligation to use thousands or millions of elements and still not be able to represent this correctly. In fact, what people observed is that you get response which is mesh dependent. The more elements you put, let's say, the more dissipation or the more or damage you get, and it seems never to converge. So this was the topic which kept people busy for a number of years, and they come up with a topic that we call here material instabilities. This is the fracture failure process, and then the localization limiters, how to handle this in terms of computation by the finite element method. So basically, the little title of this is, I'll comment on that very quickly, is when you study the fracture and failure, you have to take into account heterogeneities. As much as you can pretend the material is homogeneous, and you could do homogenization, which was a kind of a development that kept many people in France in mathematics and mechanics busy. They have this homogenization theory going from one side. People like German and his collaborators, Suki and Nigen Coxon, Zawi, and so on and so forth. On the other side, mathematics, Jacques Louis Lyon, Sanchez Palencia, and stuff like that. They actually can handle only the elastic response, some of the slight hardening, but not really localization, because homogenization is completely contrary of localization. Namely, the fracture is very sensitive to the particular heterogeneities, and you cannot pretend to ignore heterogeneities. You want to be able to deal with the structure, especially something called size effect. That is explaining why the big structure built to the same material is not going to break in the way that a small specimen built with material is breaking. So we'll first study the structure level and then the material level. Let's try to dwell into this a little bit. Lots of this work comes from a long-term collaboration with Electricité de France, which is even at present, I think, the biggest French company. We first started collaborating with Electricité de France, then we went to the nucleus, to the atomic energy, Commissaire d'énergie atomique, basically, which is kind of scientific branch of this Electricité de France. Then we went to Areva, which is a private company which was dealing with the reactors. Now it's split into Orena and the other part. And then we finally switched to Institut Radio Protection Sûreté Nucléaire, which is the government institution. Autorité Sûreté Nucléaire is the government which gives the codes for keeping these nuclear power plants. And IRSN, this institute is actually scientific branch of this Autorité Sûreté. So the goal was what? That was to keep these nuclear reactors operational from 30 to 60 years. That was the case before Fukushima. So this is your typical nuclear power plant. This beautiful structure here is a cooling tower. It's hyperbolic paraboloid type of shell, 110 meters high, typical type of installation with very complicated loading program. And since we worked on shells, every time I discussed with Electricité de France, we had a joint laboratory. So every year they would give us 2 or 3 theses. Many of these people were working funded by this type of thing, and then they got jobs, several of them, in Electricité de France type of environment. So whenever I suggested that we study this, they said, no, we don't care. This is just for cooling. And every year we can afford to lose one of these towers. It's not important. What's important is ugly duck. This is very heavy, strong structure built over reinforced concrete, pre-stressed concrete. And then there's this side layer of steel, and inside sitting a reactor, nuclear reactor. And the goal of that is when it happens something like Fukushima, God forbid that reactor would explode uncontrollably, that the cracks that are appearing in this containment structure are not huge one. So basically by having one huge crack, this would be definitely the same thing like having no containment structure whatsoever. And then all the dangerous substances would flow into the atmosphere directly. So the goal is to see, can we actually get spacing and opening of cracks, and preferably influence that they are very tiny and nicely spaced so that the loss of cooling liquid in the case of extreme accident in nuclear power plant is minimized. We had experimental results, of course, going over to the end with the reduced size. It was 1/4 of the size that was done in Sandia test, where you kind of get the cracks of this reactor and then final failure and so on and so forth. But predicting the final failure, I would say, is definitely easier than predicting the crack spacing and opening. And this is the type of topic I wanted to discuss with you today. So this was also important for earthquake. It used to be the time where many people doing experiments, this is something like a shaking table test, were just happy to get base shear, that is the total reaction in the shaking table, and present how this is changing in time, and then have a simplified model of high-rise building to be like a cantilever. Then my predecessor in Kashan, Jackie Mazar, started the project where he tried to sell the idea of a damage model, because he did thesis with Jean Lemaitre, using this damage model to say the damage modulus is equal to E times minus little b. And then he said, if you have a shear walls, the damage should be spreading inside the wall. And in fact, not only being like a bending concentrated in this base, and so that you can have a kind of higher load-bearing capacity for the shear walls than actually what is normally taken. So we had to kind of study how we can get this failure pattern in the shear walls. That's not necessarily the same as a beam bending. And then Also, eventually, you had to get like a hysteresis loops of the stress strain diagram, which is much more complicated than really like this is something that I was telling you yesterday with the PHL type of work, we were able to match that. Then you can do the same thing with the steel type material, starting from the very low scale. That means you can take a typical behavior of the steel with the sigma epsilon stress strain diagram with lots of ductility, with yield stress and so on and so forth. And then you turn this into a structural model. That is also something we'll discuss. So for me, it started 1 year after I came to Colonel Superior in Kasha. 1 year later, in the year 2000, we had the benchmark competition where Electricité de France asked that we present what kind of damage models we have so they can purchase those. And in this competition, I think everybody who is anybody in France in terms of laboratories dealing with this problem participated. Then many people from Germany, from Spain, from US, and so on and so forth. So since I just came, the way it works in French system, I inherited 3 of these lecturers who were trained by my predecessor, Mazar and Pijou Cabo, who developed these damage models in a local version. I will talk about that in a moment. And basically I said, okay, let us just use the stuff that you have and we'll basically present what you got. So it turns out Benchmark was actually presenting your results for a certain number of cases that they put together and ask you to show your results. So among all those cases, the most difficult one to handle was this case here. This was a plate or membrane rather with the 2 notches, so double-edged notch specimen. They had this kind of frame to keep it, let's say, fairly constrained. And then they introduced a non-proportional loading program where they started by shearing this plate and then basically by pulling it apart. So you can see what that provoked. They provoked these cracks, these experimental results on both facets, starting from these notches, because here you have a stress concentration. So the biggest stress that would lead to cracking would typically start from this corner. And then shearing it in the tensile world would actually produce it that the cracks are kind of making a curve that you have to be able to catch. Also, they produce the force displacement diagram given here in the red. So with the Mazar model, this is called the isotropic damage model. We could only take fitting in a way which is you take elastic response when you have no damage to fit, so have a very good agreement. And then you take the limit of elasticity, the fracture stress when the first crack would appear. And after that, you have this little d developing from 0 to 1. And you let it develop with the loading program and the mesh that is presented here. And basically, the result force displacement is given here in green. You can see a really huge difference between an experiment, which shows a much bigger resistance, and the Mazar model, which shows basically going down to 0 immediately with a very little kind of dissipation resistance. Actually, what happened here is the fact that the cracking is kind of directional phenomena. And if you have a crack, you can say that the resistance of the material in the direction which is perpendicular to the crack is certainly reduced, and the crack is sufficiently open. You have no resistance. You cannot put the 2 pieces apart, and you can put it back only with the glue. On the other hand, in the direction of the crack, the resistance often is not much perturbed, and the material is not much damaged. And so there is certain directionality in the crack, and a certain directionality that should be in the model, and that cannot be represented with an isotropic damage model, where it simply reduces the Young's modulus to the value which is Young's modulus times 1 minus d, where it goes towards 1. And then you use this Young's modulus to build elasticity tensor. Recall, you have a Lamy parameters that depend on the Young's modulus, and now that will depend on the damage Young model. So basically, you start reducing the coefficients of the elasticity tensor in the way which is not really appropriate for the kind of damage that you have here. So it took us a number of years before we were able to get much better result. Not only we can get this for the space diagram as it should, but we could get the cracks. This red here is the model that we developed later on in collaboration with the team Brancherie, Arnaud de Laplace, and so on and so forth, where you can actually have a very good representation of what is going on and have cracks. This red thing which is here, which appear to be quite representative on a real-life specimen. So this is the goal of today's lecture, to give you a little bit ingredients of one model that we developed with Delphine, and the other model that we developed with Anna de Laplace, and later on with Markoc and many other people, a sort of multi-scale model of the structure. Just to say, it wasn't only Mazar model, which was not so good. Here in the black thick line is, again, your experimental result, like the previous one in the red. And here, Arnaud de Laplace and one guy from EDF compiled all the results. And you have the results here in different colors. All the phenomenological models which are using plasticity or damage, or combination of these two, were really not on the result, and we knew the result, but it was just not possible to match it. Namely, either they will match like the peak resistance, or they will match dissipation, which is the curve underneath this thick black line, and the rest was completely wrong. The problem there is really that with such a complicated crack pattern, you have many redistribution and lots of directionality taking place. And basically, if you take finite element interpolation, for example, take a constant stress triangle, whatever you do, no matter how complicated model you put in terms of plasticity or damage criteria, your stress inside the element is constant. So basically, you simply cannot represent everything that is taking place in the phenomena of this kind. So we said, okay, this is really not good, and there's no way you can succeed this way. And so we decided to do put down certain guiding principles to construct the model. First of all, said instead of trying to put everything into a single criterion, we try to separate complexity. And in the process of breaking here, we try to identify all mechanisms that exist, and to each mechanism we give its own criteria. So we go more in the direction of something called a multi-surface or multi-criteria type of model than rather a single criteria which puts everything together. Then what was very important is to take into account the true nature of dissipation. Namely, it's one thing to have this, let's say, sliding dislocation when you start, or you have a micro cracks in the fracture process zone, in which case in 3D you can talk about volume dissipation. But once you have a crack opening, or you have the shear band sliding, this is in 3D is becoming a 2D phenomenon, because crack is just a surface. And basically, you have to take into account the dissipation now is a surface-based, not volume-based. So you have to distinguish these two types of dissipation, or the three credible. Now, this fracture and the softening phenomena is related to appearance of very, very large strain, and that basically leads to very large displacement gradients. So whatever is your finite element interpolation, if you go to very high order limits, then you have to worry about sensitivity and stuff. You cannot produce this with the classical finite element interpolation. You have to revisit the finite element method and how you build your type of representation of the field, like displacement, strain, and so on and so forth. And we talk about that also. Then finally, you'll see that this has been done in a way which is, again, relying on the method of compatible modes. So it's not only compatible modes useful for taking into account locking phenomena, but happen to be also perfect for this type of thing, or handling this type of way. And then final thing is when you're studying the fraction failure, there are many parameters you can use. There have been long arguments between whether the softening part should be like a linear softening modulus or exponential or something like that. But in fact, whatever is the modulus, it's hard to measure. The only thing you can measure is so-called the fracture energy. This is the energy you have to put into your body to take it to the ultimate limit, and then put it down to stress is equal to 0. That means you manage to tear it apart, and only glue can put it back. So this energy can be reliably measured or the most reliably measured in the typical testing environment. And then it's good to have a model which actually is using fracture energy as the material parameter, simply because this is the most reliable. So again, since we said we are going to split the complexities and give each own mechanism, that means we're going to have many, let's say, different criteria, many different internal variables, just like the one I presented to you yesterday. We had a viscosity, plasticity, damage, or whatever not, and they're going to be piling up. So then these phenomena do not have to take place at the same time. So you can go towards a typical operator split solution, where you kind of solve once, you keep the other frozen, then you solve the second ones, and so on. And then the operator solution, or in operator split solution method, what is really important is as soon as you've done the first one, you start to plug it in. And when you compute in the second one, start from the one that you obtained from the first one. So this is the type of thing that you can have. This was already the case for the typical plasticity. Here, just to recall, typical plasticity with linear isotropic hardening, or what Nigel Coxon and Halfen call the standard generalized material. The state variables are displacement, or rather the total strain, the plastic strain, and the hardening variable. And so you compute this evolution, these three, by, let's say, rate version of the equilibrium equation, d dot equal to k minus 1 times f dot. And then from that time, you get epsilon dot to be a symmetric part of d dot. Then epsilon plus d dot equal gamma dot d phi d sigma, xi dot equal to gamma dot d phi dq. Now, when you're computing this, you first get the elastic response by keeping this internal variable frozen. And then once you have this total strain, the best iterative guess, you go into computation of the plastic strain and hardening variables. This happened to be global computation that concerns all the nodes. And this is local computation takes place in each and every element or each and every Gauss point of this element. The goal of this computation is to produce the stress and the variable Q, which is thermodynamically conjugate to hardening variable psi, which allows the criteria to be negative 0, and that renders the stress field plastically admissible. Another thing which is important to say, the evolution equation of these internal variables, like plastic strain of hardening variable, should be characterized by the, let's say, characteristic time, which is much shorter than the other variables. In other words, if you have a simple tension test, you're increasing the stress and strain very slowly. And at the same time, when you have either yielding or micro-cracking, depends on the kind of material that you have, that happens very fast. And we had rate-independent models of plasticity, which basically that happens instantaneously. This was more like a diagram that corresponds to viscoplasticity. And this relaxation time is characterized by the ratio between eta and E, basically. So it goes down as quickly as you want. If eta is equal to 0, again, it goes down instantaneously. So these are type of constraint that you want to follow. There's actually two kind of space scale, and there's two time scales. And we are computing such a problem where you have an evolution of different variables, including internal variables, and you want to build this all the way to the localized failure. So we have to motivate this for particular materials. So here I took the one that was of interest to protecting nuclear reactors, the containment structure, which was reinforced concrete, and we study localization fracture. But this type of material is rather similar to many other composite materials in aerospace engineering. You have this carbon fiber reinforced polymers or whatever glass fiber. In many of these wind turbine blades are available with the glass fiber, reinforced polymer, and so on and so forth, because carbon is very expensive. So basically what characterizing those guys is that you have very long fibers, which are much stronger than the rest of the matrix. Here the matrix is concrete and the fiber is steel. So steel is certainly much more resistant than concrete. You talk about 20 times more resistant to tension, and it helps to improve the performance of this reinforced concrete type of composites. It's just the same way like a carbon fiber reinforced polymer. The carbon fibers are there to keep the resistance to traction. So now, if you really want to be able to study the fracture or structure that is built of such a composite material, this becomes like a multi-scale problem. And then what kind of scale meaning the precision of the description of your model, you have to take into account, depends on the goal you have. So first we start with a study of structure integrity. In this case, you have a structure scale, or reinforced concrete structure scale, where in order to build a real model, you have to deal with the concrete and steel, eventually the interface, bond slip between concrete and steel, in order to really describe everything that's going on. Among those, everything is definitely crack spacing and opening, which is one of the most important type of data that we are after. Now, in this approach, concrete is some kind of grayish homogenized mass, which is certainly not the truth. So if you really want to be more credible in building a fracture and failure of concrete, then you have to come to the finer scale. You have a better glasses to enhance your vision, and basically you can get the concrete is certainly not a grayish mass, which is homogeneous, but it consists of aggregate and cement, and then interface transition zone, voids, water, and so on and so forth. So in order to build a credible model, you have to distinguish between the aggregate and cement because they behave in a very different manner. And cracks are often conditioned by what you put there to build your composite material. And then at that time, we just came to the studies of durability. For that reason, the lady called Micheline Monarin, who already came to us as a retired professor, and then she was like honorary professor. From her, I learned this, what is called NIST model, which is a product of hydration of cement, of Portland cement, which was built by a simulation of a probability type of chain of chemical reactions. And then in the cube, typical cube, which is called the NIST cube with 100 micron long. So you have 100 micron times 100 times 100. This is 10 to the power 6 micron. You have 1 million, what is called voxels, and each of those voxels could become one of the phases of the Portland cement. How do they become it? By following the chemical reaction. They are putting water from the top, from the bottom, from the left, from the right, and then your probability how they can combine. And basically, then you sum up the different phases. You have a clinker phase, CSH, CH, voids, water, and so on and so forth. Every time I talk to Micheline, how many should I keep? She would never go below 16. I said, what the hell I do with 16 phases at the scale of microns? And I'm interested in something which is long 1 kilometer. So you have 10 to the minus 6 to 10 to the plus 3, and you start with 16 different phases. And every time you try to negotiate, she said, no, 16 are very important. So the idea is really like if you wanted to study durability, you have to start at this scale of micron and then see which phases will be the most sensitive to the time. You have something called lixiviation, decalcification problem, just like in the people who get old, you have osteoporosis, the bones are no longer so strong. And it's the same thing, concrete is also kind of natural material. So basically you have to combine from 10 to the minus 6 to 10 to the plus 3. That was a very, very nice project, but unfortunately Fukushima happened and that one we stopped, but there are many others what they have. So if I go now to the structure point of view, another thing that I have to take into account, I want to build, let's say, a credible model for predicting the ultimate limit load of a reinforced concrete structure. Let's say for illustration of a nuclear, but you take transportation. So one of these long bridges is a perfect example. So if you simplify this way, like it used to be, civil engineers were doing the job, a bridge is just a beam. And if you have basically just these supports on the two sides of the river, you can still have a bridge. There are many bridges that have only two supports on two sides of the river. Well, this one happened to be much longer, so many of these columns. So this is not a simple beam, but it's a continuous beam. So if you know a little bit about beams, and I hope at least you at once in your life simplify story about beams, you know that these are statically indeterminate structures. You have too many supports. These columns are also contributing to the thing. And basically, if I had removed all the columns, I just kept these supports on two sides of the river, the beam would be still okay. Maybe it would not be able to carry as much load as I want, but it would be still statically indeterminate structure. So if I want to compute the ultimate limit load of such a bridge, I have to be able to simplify this interpretation to kill and eliminate each and every of those columns to turn this beam into a simple beam and finally kill one of these supports or put a hinge or whatever it is. So this is the presentation. This is your force displacement diagram of the whole bridge. And you're up to here. And in the process, you're already getting rid of many of these columns. And getting rid of many of these columns, that means you have to be able to bring the resistance of this column to the peak and then go down to zero, where you remove the stress after the very large strain with the localization softening phase. Basically, this column is eliminated. So basically, the resistance that goes in the whole bridge is the accumulation of the resistances that you compute for removing each and every of those columns. And so you have to be able to carry out the computation where not only you have a linear elastic and hardening response, but you have this softening response, which means that the stress is decreasing, but the strain is increasing because typically the material is failing. Material is unstable and it just goes into the, let's say, irreversible type of failure. And then with these cohesive links kind of breaking. And when you get here, that means you have to put this back only with the glue. Now for the massive structure, this is even more fun because not only will you have this fracture that is leading to the stress equal to zero, but you have something called fracture process zone. We have many of these micro cracks. And basically, I mean, this is really typical massive structure. You cannot do like a karate hit and break it in one shot. You have to do shaking in different direction, which is introducing lots of damage. typically, if it's a kind of a non-proportional loading, this damage goes in each and every direction. And then for certain, let's say, phenomena like these cracks meeting each other, what is called coalescence, producing a big crack, and then you go into this softening phase. So if you want to be credible in modeling the massive structure, you have to take into account the fracture pressure zone, whereas the linear fracture mechanics only takes into account cracks. So strictly speaking, when you have something with a massive structure, you should be careful of not just applying results from the linear fracture mechanics, because contribution to the fracture pressure zone is important. Many people worked on this problem, and they needed the methods because they noticed when you put a finite element mesh, you keep changing the mesh. In normal circumstances, more elements you put, better results you get, and then you call convergence when the results is sufficiently close to the analytical result that you might use for testing your approach with respect to the tolerance you choose. However, in this case, you will see this in a moment, you actually don't get this type of result. The problem is that you go along and basically, maybe let me first do that and I'll try to explain a little bit what is going on. Well, here's your simple tension test. And then you basically put the support on this side, and then you put the force on this side. So whenever you cut this specimen, basically the force will be the same. So divided by the cross section, the stress will be the same. So typically, let me try to give you a little bit of illustration. If I take a such structure, so this is my structure, and I'm applying here a certain force F, and here's a cross section A, and I can say that whatever I cut this structure in one part or the other, I will have sigma to be equal F of A. If I put support on the left-hand side, the reaction also has to be equal to F. Nothing else can it be. So this is equal to some kind of constant. And before you break it completely, reduce it to zero, it is always constant. So if I'm plotting my stress strain diagram, this is epsilon, this is sigma. I take one situation where this is a yield stress equal to sigma y. And after that, you have hardening. If you want to do a better type of control of what is going on, I'll take my stress strain diagram. And in one of these sections, let's say somewhere here, this will be not sigma y, but will be just 1% smaller. Why do I do that? Well, I take into account heterogeneity. And basically also, I can better produce my finite element mesh, so it can go along. So when I start loading, as soon as sigma reaches 0.99, this one starts yielding. So the next step, this one will go into elastoplastic deformation, and this one will still kind of at the level of so I will have, like, for the hardening part, I have this one here, and there's just a tiny bump, and then everything else will be the same, which corresponds to this epsilon y, let's say. And here I'm already a little bit more than epsilon y. So basically, the idea is that when you have hardening, I can reach the same level of stress, and they can catch up, and only this little bump will always appear, but you can ignore it if it's not too big, and everything's fine. Now imagine that you don't have a hardening, but you reached with sigma y the peak of resistance. So up to sigma y, you are loading elastically, you're going up, and after that, this is the end of the story, you're going down. So basically, this is your elastic loading, and this is your plastic loading, but it's in the phase where you have a softening. That means that was the end of the resistance. I didn't have any, let's say, more resistance, and I go, poof. That is enough to take a linear isotropic hardening, and you take a K value to be negative. Not 10%, not 0.1 E, but you take minus 0.1 E. So this will still delay, the still will be E times K divided by E plus K, only K being negative, this will be all over that one negative. So imagine now again, you have weakened the other guy. And so this is not sigma y, but this is 0.99 sigma y. And then you go down. So this was elastic loading, and this is your plastic loading. So what happened this time, when you reach, now this is your epsilon for hardening. And let's see what would be epsilon for softening. Epsilon for softening case, you would have like this. You would reach 0.99 sigma y divided by E. Up to there, everything is fine. And then when you move beyond this, first of all, you have to do a kind of a control with the deformation, because once you pass the peak, you can no longer go around the force. The only way you can stabilize the specimen is by imposing the deformation. That's what you do in the testing machine, because you keep one end firm and the other one is pulling. Basically, in the softening part, you're already there with a very large deformation. So this would be your, let's call this epsilon 2. And what happened to these? Well, these never really reached limit of elasticity, so they simply went back. And they had the same level of stress. Like this guy, stress is still constant, but the strain is just this little tiny thing. So it actually left even smaller than the epsilon y. It's just unloaded. So the strain field is something like that. And now, if you want to represent this type of thing with the finite element method, you would need to take into account really very large displacement gradients in order to get this under control, which is definitely not so easy. A single element will not do it, that is for sure. So basically, just to give you a glimpse of that, what happens is the more elements you put, for example, you know, stress is always constant, but you put something like whatever, 3, 7, 15, 25 elements, the strain profile is such that basically only one of these elements, which is weakened, plastifies, it goes down to softening, and basically only that one gets a very large strain, and all the others unload elastically. So if you now take this one to usual finite element computation, the dissipation is the length of the element which is plastified. So as the mesh gets smaller and smaller, the element gets smaller and smaller, the one which plastified. So integrating over something which is very small, you get something close to zero. And basically, finite value of strain integrates something very small, it becomes something very small. And so you can see for the spacing diagram for different sizes of the mesh, that's like for whatever, 3, 7, 15, 25 elements, this curve goes steeper and steeper. Theoretically, if you were to put an infinite number of elements, you would go up and you would go down at the same curve. You would have no dissipation. But this cannot be representative of the real fracture phenomena, because you know by experiments that if you want to break whatever, even piece of paper, you kind of have to put some edge. So basically, this was obviously a problem, and that led to something mesh-dependent, mesh non-objectivity, mesh-dependent simulation and stuff like that. So instead of converging with having many more elements, you start actually getting something which has no sense. You go to zero. So people have noticed this, and they tried for a long time to take care of this. So one first thing, and you have this in chapter 8 on my book, so I jump now from chapter 3 to chapter 8, because I thought once you know plasticity and stuff, it could be a convenient way to finish it off. Basically, the idea is that we don't have to know about large deformation, although theoretical deformation are large, but we'll do that starting Monday. So basically, the idea here is that since you're fresh with the plasticity and damage, that you can build on top of that. And for those who are interested to do this all the way to the end, it's actually they can follow a little bit better. So the idea is like, first, what they did is this goes back to the first work of, let's say, Hilleborg et al., and then many people picked up on that with the Wilhelm, Kaspar Wilhelm, Nena Bitch and stuff like that. They actually did something called crack band model. So they built, let's say, the softening modulus, which depends on the mesh. In other words, if you really wanted to do oops, yeah, I wanted to get the same word, but doesn't matter. If you really wanted to get the proper type of behavior of the imposed displacement with respect to force, and you always have this one to this one and over there, this was something like a K index H times E divided by the K index H plus E. And then you can be sure that what is underneath is the type of dissipation that you really wanted. K index H, that means that your softening modulus is dependent upon chosen mesh. But that becomes crazy every time you run a different analysis. You have to change the parameters, and you cannot do mesh refinement automatically and stuff like that. So parameters should not and cannot be dependent upon the mesh, because parameters are something intrinsic that has behavior of material in the continuum setting. But this was really the fact that, as I said, there's this deficiency, so they can have like artificial, let's say, reparation. Another thing which helped is that you have models with viscosity. Basically, instead of plasticity, you take into account viscoplasticity, in which case the dissipation in this job enters also this viscous parameter. And so happens if you really want to keep stability in your computation, you can then pump up this viscosity coefficient. So you then viscosity coefficient gets eta index H, where H means the mesh gradient and time step and stuff like that. So the idea is really like, again, you're kind of cheating. You're changing the parameter as you go along with the different mesh and different time steps in order to keep the material stable. So both of these remedies, I put them in the book, not to advocate that they should be used, but if you have a classical coach who doesn't know how to compute fracture, if for any reason you have to compute fracture, this is two ways how you can cheat under quotation marks. Namely, you choose your parameters in the way that you need for the given mesh, and then you can have some kind of meaningful results, at least for that different mesh, for that mesh. And if you change the mesh, then you have to know how to change the parameter and so on and so forth. But if you have no other way, what the hell you do what you can, basically. I mean, if you cannot do perfectly, you do it anyway it takes, just in order to be able to solve some problem. Now people learned about that and they say, well, this is not good. And they started doing better models. So what are the better models? One of the better models is so-called Coursera media. It was used by Mulhouse. It's a German guy who worked for a long time in Australia and also divorced. Is a Dutch guy who's now in England. Basically, the idea is that it has been noticed, these guys who worked for soil mechanics, both of them, because in Austria, this mining is very important. And in Netherlands, it's about the level of the country is below the sea, so water is always there for the saturation. So all these soil mechanics were very important problems. And they turned out that in soil mechanics you can use Coursera media. Coursera media is a very famous work of two brothers, F and E Coursera. I never understood what is F, what is E, maybe François and Eugène, whatever. And they came up with a continuum mechanics formulation that had not only displacement field, but attached to that rotation field. Then Nagdi, in his book on shells, he used Coursera media as the basis of developing the shell theory directly from Coursera media. So you can imagine, we did recently work with one of my former doctoral students, Sarah Gilchich, who just published another one on a solid instructions paper, so-called micropolar media. In macropolar media, you take into account not only the rotation field and the strain for that one, you also take a curvature. And then you really get like a shell type of thing. So basically, these type of things are kind of heavy to do because typically in the engineering problems, rotations are not of interest. And you have tendency to eliminate them because who cares what is rotation? We typically need control displacements and then stresses and things like that. So having to introduce this rotation, this is already a hassle. The equation become more complicated. You have to provide certain parameters, which are not an easy job. This was in the work of Sarah that she defended maybe 2 years ago with the still papers coming out. And basically, on top of that, it was not efficient for each and every mode of failure. It turned out it worked only for mode 2, that is the shear, and not really the attraction. So then people went to the school of Bajant, who started work with a Chinese student, Lin, I think, for plasticity, and then my predecessor in Kashna Pijikabo did the same thing only for damage. They did so-called non-local model. So what is non-local model? Well, basically, they have done this. If you are computed the stress trace diagram, you take, this is your sigma epsilon, and you want to have something which is suitable of doing like this one, and then hardening, and then going down to softening. So from that on, you say this is your point X, but, and this is starting failing, there's a crack. So you take like something like a characteristic length, L index C, and you compute epsilon of X, which is the value that you need here, by summing up, that means integrating over the circle or sphere, if it's 3D, of of this one with the characteristic length. So basically, if this is really your strain field, because you have a crack, you're kind of averaging. And what you're doing in the process, really, the whole strain is happening in this crack. That's actually the material starts separating like crazy. But if by integrating over characteristic length, you're kind of borrowing the material from the neighborhood, and you're averaging so that you can have a strain which is kind of, let's say, reasonable and not huge, like you should have. So the problem there, you have something called non-local theory, where the strain is obtained from a non-local measure. Is not epsilon x, is not just du dx, but it's like an average of this strain over a certain neighborhood. In fact, I asked Pijlekaba, what do you take as a typical LC? I said for concrete, we take three times the grain diameter, the concrete. But the grains you have like aggregate, you have big and small. So which one do you take basically? And then when he left and I replaced him for 1 year, when he was coming, most of the time I was helping with his students. And there was a young lady who was working for this, and they were studying this non-local damage model to get identification of these results for the 3-point bending test with the specimen with the notch. So if you start breaking here, he would take like this one here, and then in the strain that you want to average, you get the strain at the other side of the notch, which is a little bit crazy. What the hell? When you have a notch, when you have a crack here, obviously these two strains become quite independent. They kind of separate because they don't talk to each other. The crack put in between. So there are many things you can criticize, but anyway, that was the way they were doing it at the time. So no local model where and then in the code used by nuclear industry, code custom. Well, now it's called CAST 3M, like for third millionaire. They have this Mazar model, E times 1 minus D, with a piece that was done by a no-local model, putting this characteristic length and stuff like that. They might have similar thing in the Codaster that is used in electricity de France. Then they realized that the same trick with no-local model, you can do it with the gradient model. Basically, like, go from the crack band to viscosity is the same thing here. In which case, the plastic multiplier does not come from a equation saying phi of gamma equal to 0, which is algebraic equation, gives you gamma at certain time and plus 1 directly. This one was coming now from differential equation, and you have to solve differential equation in the weak form and so on and so forth. So we have this gradient, plasticity gradient, damage and gradient, this gradient, that, and whatever. So there are lots of works in this kind. The problem there is that you have to know what is the boundary between elastic and plastic zone in order to set the boundary condition for computing this plastic multiplier. In particular, you don't know it. And then there's an equivalence between non-local and gradient model. So you're doing the same thing, only you're developing some kind of, let's say, asymptotic development and stuff. So there are lots of arguments. I talked to Milan Irashik from Prague, who was at the time in Switzerland and came for 1 year. We overlapped. I was leaving and he was coming. And he told me he was also a Bajan student because another Czech guy And they really discussed this a lot and said in many of these meetings, these two groups were arguing, but at the end they came to the same thing and basically the same trick. So none of these methods, I would say, anymore is really desirable. What finally won is the one which was really needed. In fact, when you have a localized plasticity, you have such a high gradients of displacement field that not a single element can represent that correctly. So what they've done by starting these works here, they introduce the discontinuities. Either introduce the strain discontinuity, you do it 2 times, so you have a shear band, or you introduce displacement discontinuity, so you have something that looks like a crack. And that basically that we've done here as well. In other words, this is maybe in this picture here. What you do, maybe I could illustrate that as well again. What you do is what the hell is this? Okay, so what you have it like that. Basically, I have it this one, and I have some kind of a crack appearing here. So I take a finite element. I take usual 2 shape functions, n1 and n2. And if I want to represent the crack that goes into that, I take a Heaviside function. So this is h at x bar, this being your x bar, the given location where the stuff occurs. So this is equal to either 1 when x is larger than x bar, and it's equal to 0 when x is less or equal to x bar. So basically you get the displacement jump, which is going to describe this crack. And indeed, it corresponds to something that we have done intrinsically, because you could see this strain profile, it gets more and more sharp. So in the, basically now you take the displacement to be n1, u1, n2, u2 plus this Heaviside times the displacement. So if you build the whole displacement thing, that would be something like, oops, let me put it here, maybe like that. I will have this is u1, then I have a linear interpolation, then I have a jump, and then I have another linear interpolation and put it there. So what's kind of bad is this will be parameter, and it will be like u would be equal to n1 u1 plus n2 u2. This is your usual interpolation, where u1 and u2 are nodal values. For example, this is your u1. And then plus, you put this Heaviside function of x at x bar times some parameter alpha. So this here would be your alpha. And here would be u2 plus this alpha. So if you do this, it turns out that every adjacent element has to know about your alpha. But another trick would be, okay, forget about that. I keep this one to be u2. So this is just the u2 here. And I put this one in terms of what's called embedded discontinuity. So the profile now is this one, and this is still my alpha. So now alpha becomes a parameter which is used only for particular element. So in 1D case, it's really inside, so nobody worries about that. But in 2D, 3D case, alpha becomes something like a parameter of incompatible mode. The only difference, incompatible mode is not quadratic function for Q4 node element, but it's like this jump function that takes into account the representation of discontinuity in displacement field due to the crack. Other than that, the method of incompatible modes applies perfectly with all the logic that is in there. And that's what we used in the long term to kind of implement that. Now, the difference from what other people are doing, and the thesis of Delphine Branchery, what we've done, we also accounted for the fracture process zone, because our structures of interest were massive structures, which has this fracture process zone. For this case, you're still hardening, and then you go into the softening with the crack. So you could keep hardening if you have a 2D, 3D situation, the crack can be developing in one direction. At the same time, fracture zone can remain active in the other direction where the crack is not influencing. If you go to change non-proportional loading, you have to be able to handle this, the more general scenario. And that's actually what we're aiming for. So in 1D case, that came down to this. Basically, you had a like possibility, rather than having just like elastic and then softening, we had elastic, then fracture process zone for these micro cracks that are in the fracture process zone, and then you go into softening. And you unload, of course, you have plasticity and stuff like that. So what comes out of this analysis, we again go through thermodynamics with the criteria for yielding and stuff like that. We'll discuss this in a moment. But the idea is like what comes out of that is that the total dissipation can be split now into the volume part. This is the part that you normally take for plasticity, is a sigma times epsilon plastic dot plus hardening variable Q bar times C bar dot. We put the bar for the hardening. And now we have to introduce softening variable Q2 bar dot C2 bar dot. Now this is softening part. So the total dissipation is additive, being able to handle simultaneously the volume part in the fracture process zone and the surface part along the crack. Until the crack completely separated, you still have some dissipation. And in order to be able to clearly do the additive composition of the total dissipation to volume part and surface part, you have to enforce the stress, what we call the orthogonality condition, which says of a particular element, the work of the stress on the virtual, let's say, the deformation that is associated with this softening part should be equal to the work of the traction, which is opening the crack on this, the displacement representing the crack. In fact, what it says simply is that this is 2D, 3D version of the same condition, which is here. I can go up and I can go down, and until I reduce stress completely down to zero, the stress has to be constant inside the bar. In other words, the traction, which is opening the crack where you start yielding, and the stresses in the other parts of your truss bar have to be the same. So in 1D, it simply comes to that. That means that T bar is equal to sigma in 1D, nothing more than that. So basically, in 2D and 3D, of course, this is more involved. It depends what is G. G is the kind of mode that you are representing and so on and so forth. For plasticity, this is mode 2. For damage is mode 1. We'll talk about that in a moment. So this is the type of thing. So it is like development at the end. If you go through these major phases, first we did plasticity, then Delphine, where I wrote the paper, it was just late Mike Crisfield passed away, so we need paper for his special issue. And then basically Delphine wrote for damage. So we had like an elastic response here. Then you have a hardening part, and then you have a softening part. So in this part, you have a micro cracking, bulk dissipation, and this part you have macro cracking with the surface dissipation. Again, note that in 1D, they are chain reaction. If you one stops, the other one starts. But in 2D, 3D, there's no way, there's no guarantee both of them could go simultaneously. And that's at the end our final goal. So what we have done is until you have a hardening, that means elastic and hardening response, you can start with the standard finite elements. Then when you have a softening, you have to define your surface along which the macro crack will appear. And basically this surface is oriented with a unit vector exterior normal that we call N, like Nice. And then the kind of mode that you have is called M, like a monochrome. So basically the gradient, when it starts going into softening, or displacement could be written as a tensor product between N and M multiplied by a particular coefficient, which does what is the kind of opening. And so we have to handle two phenomena. One is expressing the physical process that takes place in the fracture process zone. So we talk about stresses, average over the volume. And then another one is physical phenomena taking place of the fracture surface. So talk about forces, T over this particular surface. And then you're taking the crack opening, U with two brackets here, like a displacement jump. This is what I called alpha just in the sketch before. That is basically handling this. So we'll have to provide the two sets of constitutive equation, one for the bulk part and one for the surface part as we go. So here we start. So first we need, in mechanics, we need three groups of equation: equilibrium, kinematics, and constitutive behavior. So equilibrium, we have a linear momentum. Angular momentum will be symmetry of the stress. Boundary condition will impose the stress and impose the displacement. And now when we introduce into softening, this the localized failure, we impose that the traction should not be discontinuous across this surface. This is really the same requirement when you go back. Stress should be constant along the bar. So here you have this discontinuity, crack opening, but the stress and traction are the same. This orthogonality condition will tell you that. So basically here we are saying that the jump in traction should be equal to 0. And by the Cauchy principle, the traction is computed by the stress tensor times the unit vector exterior normal. So that n being constant, once you have a crack, you don't change it. You cannot remove the crack, it's still there. Basically, then the jump in sigma has to be equal to 0. So this is the extra condition that we can use in our weak form. So when you're developing your weak form, you build this by getting the equilibrium equation weak form, and then the what you call it, the von Neumann boundary in the weak form, and plus this jump condition in the weak form, again, you enter there. So these are your equilibrium equations. The next one is the kinematics equation. Now we said we need a representation of the jump because of the localized behavior. So we introduce this Heaviside function that I just described. Only 2D, 3D is a bit more complicated. It's not just x bar, it's gamma. Gamma being the surface, which is positioning this localization type. And basically, then you take that you have a normal field that is represented by the finite element that we call U bar. This is regular displacement field that you represent with your shape functions, NA, that you chose for particular element. We studied the three node element, 4 node element, and so on. So you can take the same ones. And on top of that, you have this parameter U2 bar, function of time times the Heaviside of gamma S. Heaviside gamma S is the function which takes a value 0 before you reach gamma S. And then after you pass gamma S and all the way to the right, it takes a value which is equal to 1. As I said, having such a construction, then each and every element which is next to this element where the failure occurs would know what happens there directly, and they would have to share this U2 bar for one element to another. This would be becoming global. There's a trick that you can turn it into local, turn it into the framework of collateral modes, simply by reducing the Heaviside to something which has a 0 value at the nodes, so you don't go beyond the element. And basically, this is the method that we call embedded discontinuity. So you still have discontinuity, but remains embedded inside the element. So many people argued what we are representing is some kind of element-wise representation of the crack. This is not the most important part of this method. What we are representing in the proper distribution of the strain field, the fact that it localizes, that it has very large values at certain point in time, and basically not necessarily that is really like a representational crack. What we are seeking in the best representation is the representation of dissipation, and the finite element for being the best method representing the energy also is the best method representing the dissipated energy. And we'll see that with the embedded discontinuity type of method, we have really the best representation of dissipation. And indeed, which is not the same. You have something called XFEM with the representation of crack global on top of the finite element mesh. Here's just element-wise, and you don't compare the pattern of the cracks in one with the other, because that's really what not counts. What you really compare is the dissipation, because that's what method is giving you the best way. So in the global way, this is also when they have now the other interpolation, like this phase field approach, and using these isogeometric elements, you can have a very nice smooth shapes for curvilinear stuff that comes from this Pixar type of movies. They introduce these nerves and so on and so forth. But as I said, for finite element, it's not really a big advantage because you lose the partition unity. You use guaranteed to develop your solution in terms of analytical function. It can be perfect for certain cases, you know what to put, but not so good when you have a more general situation. In any case, what they have is a really problem getting this phi. In the embedded discontinuity method, there's no problem whatsoever because you do it at the element level, and turns out phi is a combination of the shape functions which are outside of this element. In other words, if I take it here, oops, if I take it here, you see, if the crack splits this part, this phi will be a summation of the shape function which are to the right of the set. So there's like all this and omega plus being in the orientation of the unit vector exterior normal n. This is omega plus and this is your omega minus. So basically I sum up all this. So if I'm cutting here, then it will be like 3 nodes. If I cut here, it will be 2 nodes. If I'm cutting somewhere here, it will be only 1 node, and so on and so forth. So every time I can very easily construct this modification of the Heaviside function so that the influence of Bethe discontinuity does not go beyond the particular element. Okay, when I accepted this to be displacement field, I now use the standard way to obtain the strain field. In other words, I take a symmetric part of the displacement gradient. So I have a regular part, which is the same as the typical finite element approach. And I have this discontinuity part, which brings this Dirac. So the derivative of the Heaviside function is the Dirac function. What is Dirac function is you take any function, multiply by Dirac, and integrate from minus infinity to infinity. You get the value of this function at the point where it is. And so that means that the strain is localized at the discontinuity, basically by using this Dirac. In terms of orientation, there's no strain any other place but at this discontinuity. And this strain is written in terms of symmetric power displacement gradient, which you can write as a jump of the displacement, tensor product with n being the unit vector exterior normal for this discontinuity, times Dirac. So this is your strain field. Well, basically what we have discussed here, it's more like a somewhat strange representation of the plastic deformation. And why is it strange? Because when you go into softening, because of the analysis I was doing it for 1D case, obviously, you know, the strain becomes very large where the softening starts, and it unloads all over the neighborhood. So basically, that becomes a very large plastic strain, and all the rest is going into the elastic strain. So in the stuff that is done, all the rest is also giving a fracture process zone, as opposed to having just this softening part. So again, this becomes a sort of additive decomposition of the total strain to the elastic and plastic. Only the plastic strain has been localized to a particular discontinuity. And then you get in the business of doing your plasticity because you just need elastic strain to do stresses and so on and so forth. So it's not that complicated after all. So basically now the last stuff is, okay, how do I actually get the constitutive equation? So as I said, we have to do both bulk dissipation and localized dissipation. So bulk dissipation is the ratio between sigma and epsilon, and localized dissipation ratio between the traction and the displacement discontinuity. So one way of doing that is that you say that discontinuity of the traction should not occur, or discontinuity of the stress should not occur. So basically, then I'm saying that this could be C elastoplastics times N, and given that what you have here for the U times N2 bar, when I go through all this development, I can work out that at the end, I have something which says N dot C elastoplastic N times M, the type of mode. M is a U2 bar divided by the norm of the U2 bar, has to be equal to 0. So this A elastoplastic, which is produced of the unit vector exterior normal N, and then dotted with the elastoplastic tangent modulus, is so-called acoustic tensor. Basically, it says that the kind of localized failure that would occur has to do a lot with the type of material that you're talking about. If you talk about steel, which doesn't like shear, which is sensitive to the vectoric part of stress field, when you come to localized failure, it's not likely to have a crack. It's more likely to have a shear band, because M happened to be, if you solve this eigenvalue problem, if this is actually eigenvalue problem, A elastoplastic minus lambda times identity times M, where lambda is equal to 0. This is the instability where lambda is equal to 0. And so basically, if I compute what is the critical mode for this instability, well, it turns out for the, what you call it, the metal type of materials, the typical mode is a shear where M and N are perpendicular. That is, M is orthogonal to N, and their scalar product equal to 0. And if you take this instead of elastoplastic modulus, if you take a damage modulus with typical, let's say, damage criteria related to kind of bulk deformation, so on and so forth, basically they can say that the typical mode of failure is mode 1, where N and M are parallel, and it's simply you open the crack in the direction of the principal stress. So these are two types of models that you develop, one for plasticity, where the J2 plasticity of diatonic stress and so on, so for reaching the limit, and then going to ultimate stress where you go to softening, then translates into the mode 2 failure, shear bands, and then we developed also damage where the isotropic damage goes into the active crack that is opening in mode 1, and then goes into this type of failure. So here's the type of constant equation for damage, the paper that was written by Anna. Then we identified this parameter of such a model with the work by Anna Kucherova, a later thesis after Delphine. So the idea was that you can have the parameters to describe the damage in the volume. That means you need like damage compliance, and you need a damage hardening variable. And here in the discrete model that is for discontinuity, you need a damage compliance for a softening part, and you need a softening variable C2 bar. Here you need a regular strain to describe what is going on in bulk, which is epsilon bar, that's computed from the symmetric displacement gradient of the regular displacement part. And here you need this displacement jump that is giving you the localized failure, and basically you are getting the crack opening. So state equations are, when you need the stress, you compute it from the d bar minus 1 times epsilon, and here you will compute your traction from q 2 bar minus 1 times u, and hardening and softening variables have the same type of feature where you choose this hardening modules and softening modules to kind of define the proper definition of the fracture energy. That's actually what you use the parameter. These are always computed as a function of that. The function that are saying when the fracture process now starts is given here. So we took something that is in fact very similar to a Lemaitre model. This is so-called isotropic damage model, where you keep an elastic part of damage compliance, which is elasticity tensor inverse inside, to give you the proper norm of the stress tensor. And you compare that against fracture limit or limit of elasticity. And basically, this is the same thing as saying that I want to have something which is in each and every direction, which is kind of reasonable, because if you fracture process on typical micro cracks, they really go into each and every direction. So the fact that they are isotropic is not a problem. What becomes problem is after you reach the softening, then obviously you have a crack, you have orientation. You have to choose your unit vector extreme normal and not move it anymore if you really want to handle crack properly. So that's what we've done here. Basically, once you reach that one, we then had a two surface plasticity type of model for the softening. We have a N component of destruction, which is the one which is opening the crack. We compare this against the value of the ultimate stress when the softening starts. And you have this softening variable Q2 bar, which is accumulating this thing. And on the other side, we also put a second criteria, which allows you to take into account the sliding, because you can break a surface in terms of like if you pull it only in this direction, or you can slide it and also break the kind of cohesive links between these things. So M is now in the direction of the tangential sliding that was here, as opposed to N. And so the traction of the is computed by the Cauchy principle, sigma times N. So you have two components, sigma NN and sigma NM in this Monaco. So sigma NN is compared against sigma F, and sigma NM is compared against sigma S, which would be like a limit, ultimate limit in shear. But then both of these are building their damage inside the same softening variable. Then you can combine a loading program where you have a little bit of sliding and then pooling, or if you have a first pooling and then sliding, all of these should come to the same type of thing. And that's basically, you can then compute dissipation for hardening part, softening part, which is the goal, and then get the proper amount of dissipation to this model. So all these details are in the book. They actually are put in chapter 3 already, and I kind of squeezed in the softening there without talking about softening, just to illustrate what we can do. But now with this explanation, I think you can go back and combine what I explained in chapter 8 and chapter 3. And if you didn't understand the first reading, the weekend is coming. So I encourage you to read very thoroughly chapter 2, chapter 3, and then chapter 8 a little bit none if you manage to do it. So next step is you need a finite element interpolation. And we have chosen for damage something, the constant strain triangle, the simplest one of all the finite elements. And we can say this one is really lousy if you want to represent something in terms of high gradients, because it gives you only constant stress or constant strain inside every element. So you need like zillions of elements to get really proper variation of these gradients. Now, instead of that, we simply take a discontinuity. So here's your discontinuity typically built at the center of the element. And then we can get the interpretation of our strain field, which is basically done here, where you compute the gradient of such a discontinuity. And this amounts with the finite element implementation to this G variable. So this G is very much the same like in compatible mode stuff, but only the function M is not a quadratic bubble function like you have in Q4 elements, but this is this type of function that you have to describe. It has jump inside the element. So this is your M, derivative of this M, with respect to X and Y, properly arranged like in B matrix will give you the G matrix. So I have like one on the let's say with this, when you have these elements which are crossed by this continuity, this guy is came the wrong way. So basically, when you have elements which are crossed by this discontinuity, I can have each and every of these elements will have extra function which appears there. So when all is said and done, in terms of the weak form equilibrium equation that you have solved, here you have a set of nonlinear equation that has to deliver the nodal displacements. And on top of that, for each of the elements which is crossed by this discontinuity, when you have a localized failure, you have an extra equation which is saying that the stresses in the fracture process zone should be matching the traction with the given type of work. And basically the role of this will be giving you the opening of the crack for each of the element which is activated. So this could be handled very nicely with the same computational approach like in the incompatible mode method. In other words, you have a global loop getting the best value of the total displacement, which gives you the best value of the total strain. Then at the element level, you can have this type of equation, which is following from linearizing the second equation for each of the elements. So it's done independently from element to element, because this is the feature of embedded discontinuity, because embedded discontinuity is one element, nothing to do with another element. So each element can run this simultaneously, as opposed to externally. You have to again couple it. And basically, for that one, well, you might need a proper level of stress, and proper level of stress might require, again, damage or plasticity in the bulk. So for that one, you need, if you recall, the enforcing the admissibility of your stress field and getting the yield function and plastic multipliers and whatnot. So you have basically these three loops. One is the level of I for D, one for the, let's say, J for the U, and for the K, finally, for the stresses. And you're done. So this really fits very nicely inside the framework that we already used and can allow you to treat fracture in a very perfect way. What kind of result you can have? First of all, in the first paper that I wrote, we had basically the plasticity. So what I did is we use B-bar method, which is one alternative method to enhance the behavior for quasi-incompressible behavior of a J2 plasticity. And then I could leave the incompatible modes to represent this localized failure. So you can see that if you use this approach, you're really perfect with either mesh, which is coarse or fine. You have it here. This was like a simple tension test with this specimen. Again, we had these two double notches, and they were on purpose put at the distance where the type of failure that would occur is very conducive to plasticity type of material. So first you have a fracture process zone with a, let's say this is part here where you have like some kind of hardening variable building up. And then when you reach ultimate value, you have this shear band sliding at 45 degrees, which is just perfect for plasticity. And you can see that it's not a single line, but it's actually a bunch of these lines. But what really matters, we are not chasing the lines. First of all, they have good orientation. They're not a single line. You can say, okay, well, they're not a single line, but you don't need the line anyway, because on the basis of the finite element approximation, which is already an approximation for elasticity, how can you then get the exact solution for inelasticity? This is a joke. But on the other hand, you can have the best representation for the energy and the best representation for the dissipated energy. And that's precisely what you got here. If you go to force displacement diagram, for coarse or fine mesh, one is red, one is blue, you don't see a difference. They're kind of blue or reddish, and just at one top they're showing. If you have isoparametric elements and you get a slight locking, This is not heavily constrained, so you get not too much, but still here you're not getting the right result because you don't take into account this plastic incompressibility basically before you do that. So this was already very nice for plasticity. Then we also did it for damage. Now this was done in the paper that Delphi wrote. Basically, you take the same concept for plasticity, you push it into the damage. Instead of 4-node element that we've done previously, we took a 3-node element with this discontinuity. That is the one that I was describing here. And basically, you can have, again, coarse mesh. You can have 5 so-called structured mesh where all the elements are regular. So typically, you have a simple tension test. So the crack should occur at one point. Typically, we're weakening one of these elements, so make sure that the crack occurs there, although the mesh was not specially defined for that purposes, so it could be anywhere that occurs. But you can see here what's kind of funny is that the crack is represented only by the orientation. Orientation is always right, but the length is not necessarily right because you take you sum up all these red lines which are representing cracks inside each and every element. So if you sum it up in coarse mesh, that becomes 157 millimeters. If you sum it up here, that becomes 133 millimeters. So the length of the crack is not the same, but who cares about the length of the crack? We need orientation and we need dissipation. Basically, the idea that either take a maillage grossier, that means coarse mesh, or maillage fin, that means fine mesh, the result happened to be the same. Either red or blue, everything is perfect. Then we played with this idea when you have only softening as opposed to when you have a fracture process zone. This is part of this Norumame test already, and basically we took a part of that and we ran the example. We have like a possibility to harden and then go into softening. So you can see that it develops quite a significant fracture process zone. And then after that, the softening takes part and poof, all the dissipation go into softening. This one gets blocked more or less. Or if you have only elastic and then softening, then the results is not the same. The cracks are all over the place, and definitely you need the contribution of fracture process zone to stabilize the cracks, how they propagate. Here there are way too many. Here there's like a reason of that, just like it was observed experimentally. So fracture process zone is really good transition when you're computing your stuff. Then we are doing this for 3-point bending. Basically, in many of these cohesive materials, the way you can obtain the tensile strength is not by simple tension test, because the type of material you cannot put in the testing machine, it will break. So what people do, they do so-called 3-point bending. They put these 2 supports in a simple beam and then push it in the middle. And in order to kind of master this a little bit better, they put a notch in the middle, so the cracking will concentrate here despite any heterogeneities. And that was used to identify the parameters of this model. So what are the parameters of this model? We have Young's modulus Poisson's ratio characterizing elastic response. Then we have like a limit of elasticity and the hardening modulus. And then finally we have a ultimate stress that leads to softening failure, either in mode 1 and in mode 2. And we have something that is actually allow us to quantify what is the total energy that goes into this. So in any case, even though it's written this way, I mean, what we are really computing at the end is the energy parameter that goes into that. Now, if you are not happy with the solid mechanics type of approach, you want to go to structure mechanics. This work comes from one of my students from Vietnam. I had 5 of those. This is the first one who came. He already was of rather advanced stage when he came. Ba Hung Pham. Ba Hung is a hero. So Ba Hung is a high hero. So after he finished his thesis, he organized a visit by ambassador of Vietnam and also the Minister of Construction in Vietnam. And this is a big job because Vietnam is 1,200 kilometers from Hanoi to Saigon or Ho Chi Minh City, and you have to do lots of construction. So in this visit, these guys liked my performance because I was the only one who can explain what École Normale Supérieure is all about. Because they have École Normale in Vietnam, and they don't know what is École Normale Supérieure, which is in France. And the minister asked whether it's better or worse than university. So my director, who was one of these Normalian, was giving like speech for 10 minutes explaining the French Revolution norms and Normalian and stuff like that. And then minister was just staring blankly. And at the end, when we stopped, I said, if I allow myself to speak after my president, I can just answer also your question. I'll tell you what my students told me. If you ask yourself if university is better than École Normale Supérieure or worse, École Normale Supérieure means that it's normal that you are superior to universities. And the minister said, huh. So I was the only one who got a tie as a present. Nobody else got any present. But and my student got a job of a secretary of Ministry of Construction. So when he came to me, basically the idea is that I asked him what you were doing. He said, we are constructing this high-rise building, 100 stories, and we are doing this computation with this Eurocode. I said, what the hell Eurocode in Vietnam? But what the hell? Obviously, they think it's a good code. And typically, they go into this yield, what you call the moment in a stuff, and they actually construct the yield moment like saying there's a compression concrete and tensile steel, and you have a certain value of this moment. And then you simply go into a certain number of moments, and that's. But what's wrong about that is basically when they have a yield moment, they keep this yield moment forever, which is not true. In fact, if you look into this fracture phenomena, the proper diagram should be in terms of curvature and moment, something that goes into the, if you talk about reinforced concrete, something first has a cracking of concrete, then has a yielding of steel, then has an ultimate behavior of the concrete, and after that it has softening. And you have to go down to kill this completely and not really keep it forever at NY. So basically, this was his job. So we did different models. One was basically that you do it by hand, and you introduce directly this type of diagram into this construction. And the other one, you do like a multi-layer in 2D or multi-fiber in 3D version of that, and you can simply feed every fiber either concrete or steel behavior. Of course, this one takes more time, but it has a more, let's say, features for this one. And then finally, we also did this one for predicting the crack spacing opening, but this is another student, Amar Bukretuz. Then after that, he started working forever. He did thesis for ESN, but after that, he didn't like to work for the state. It was better salary forever. So let me just explain a little bit quickly. First of all, the Timoshenko beam is a kind of very simple model where you can have a interpolation of the rotation of the cross-section theta given to be a two-node element linear. And then if you want to have like a jumping curvature because of the plastic hinge, you have to introduce this heaviside function just like when you have this, let's say, a fracture in a bar. So here it's really like the bar, only the thing is this is not for the rotation field. So theta of x is n1, theta 1 plus n2, theta 2. Then you introduce heaviside. If you want to break it, and you put this alpha to be the change of rotation, which is not smooth because you have a breaking. And then you can actually eliminate the influence of this beyond certain element. You turn this into Benny discontinuity, this parameter alpha. Then you get the curvature to be regular part plus this Dirac part. And then basically after that, you can get your interpolation of the curvature. You have to do it to make sure that patch test is verified. So you have to pull it into certain normalization. So for every element which gets plastified, you have an extra equation to be solved. Extra equation giving you basically the moment in the bulk and moment and the discontinuity should be matching to be the same moment. This is it in here. And all the other equations are the usual equation for the beam equilibrium where you have a normal force traction and then shear force and the moment, and you're basically computing all this. So we were able to use this to check some works for Codaster. So this is your typical finite element model of the reinforced concrete beam. What they use, they had the experimental results. So Luc Deven was running this thing. He was helping with it. It was one of my lecturers, probably the best one there. And we were able to show that as opposed to Codaster, you cannot go further than that. We can do all these shapes perfectly and get kind of good matching with respect of this type of thing. Then another Vietnamese student, Bui, helped with another Vietnamese student in Goa, generalize this not only to the bending hinge, but also to the shear hinge. So if you, this was the benchmark competition done by this people from Swiss Federal Institute of Technology in Switzerland, in Zurich. And the professor was retiring, he was expert on this shear failure in concrete. So they did on purpose, designing it was very poorly, so the shear failure would occur. And they were testing this at that time. I was visiting, so I could take pictures because we matched these results in everything because we had the experimental results. And basically what was the trick? This was the bending, let's say, failure. If you want to have a shear failure in the Timoshenko beam, you need a transverse displacement and introduce this jump. And then basically you can have a shear hinge on top of the bending hinge. So you can simultaneously run the analysis where you can allow for the bending hinge and the shear hinge So you can have really U, V, and theta, like three displacement components for bending. So you can, the axial, shear, and bending, you can get any hinge you want. So he's like playing a different type of scenario, either if you have only shear hinge, or if you have a bending hinge, or if you have two hinges, and so on and so forth, you can go along. This one, maybe I'll stop because this is really the most subtle part. Well, maybe I could say that as well. The trick is like, if you now come to a reinforced concrete, and this is now follow-up work with Amor Buketus, who was doing his thesis. Amor Buketus is normally a guy, very intelligent, but a little bit lazy. So he was just very quick in the conferences we were doing. They all came together. So he was talking to the guys who did this before him, Delphine Branchery on the concrete, Roberto Dominguez on bone slip, and he put it together, and very quickly had results. Then got a good job. And what can you do? You have to be intelligent and lazy, and sometimes he gets all this. But the idea, and I had to write a paper, but then it was at least better written. So the idea is as follows. Now you have reinforced concrete. And we have explained in detail what do you do when you kind of break the concrete. Here you see the fracture process zone. This is 4-point bending test. You have these two forces, and then you have these two supports. If you recall, the moment bending, the bending moment diagram is like a constant in this part between two forces, and then linear going towards supports, and the shear is only in these outside parts and zero inside. So basically, you can see that the model we have can predict everything. And basically, this model can predict that you have like a breaking and the bending part, which is vertical cracks. And then here in the inclined part, these are like a shear cracks. And these are really like a perfect result that you can make. And then what you need is a representation of the bond slip. So representation of bond slip, given that we know what the steel is, was done by this extended finite element method. I'll come to that in a second. Basically, this is the part where you have a connection on top of your displacement. So at the normal node, you just have displacement degrees of freedom. But the node where you attach the steel bar, you also have a bond slip. So you can have a choice between either taking displacement of concrete, displacement of steel, or you can represent that and bond slip with difference of these two, or you can represent it by taking displacement of concrete and the bond slip, and then steel will be concrete plus slip, which is the case that we took. We call this relative displacement. So now you have a extra equation, which is giving you redistribution of the bond slip. And on top of what you have there, cracking of the steel and cracking of the concrete, and in every, you have incompatible mode, and you have a stress and stuff like that. So there's extra loop, which is semi-global, as global as you have your steel, but you start getting results that you don't have in any other code. This is the code that we develop for us to radio potential and nuclear, so they can check what these guys are doing in Electricité de France with code Astel Custom. And Amor was supposed to be working for them, but then decided to go to Areva. So they have a code. Frankly, I'm not sure if they have anybody who knows how to use this code, but in any case, the idea is like the code can do this. And basically what it can do, they can really teach you how the reinforced concrete does. If you have very strong reinforcement, every crack is just small blimp. If you have weak reinforcement, like Mike Crisfield, who worked first for civil and then to aerospace engineering, he studied this with arc length method. You really need something that allows you to go with a peak every time you jump over there. So we were able to validate this. There was a testing that we got in touch with people from École Polytechnique Fédérale de Lausanne in Switzerland, and Bruckwiller and his team, they were able to do this so-called tie beam test. You have a steel bar which are very long, you pull them, and then concrete which follows, at certain point starts cracking. First of all, you can see here force displacement diagram they measured, and opening of cracks is very interesting. When the first crack opens, it propagates, then second opens, the first one closes a little bit, the third one opens, the first two close a little bit. And so basically we matched the first that opens, and we get force displacement diagram, which is perfect. The opening, this goes like I described. The first one opens, second one opens, first one closes, third one opens, the first two close a little bit. And basically this is the key result. This is redistribution of bond slip. So basically when you have a first crack, you kind of slipping, then you have a second crack. The one second is, first one is closing, and then you have a third one, the other two are closing. So this bond slip redistribution would automatically give you the crack spacing and opening as you go along. So this is really the type of thing. And then we were playing with the heterogeneity. If you have this type beam test done in France, this is thesis of Daoud, I think it was done in Lyon, and with a different type of specimen, you can see the crack spacing is not uniform, but it varies from 14 to 19. So in Norberto Dominguez thesis, we're playing with these different things. And basically, it's important to put bond slip, otherwise you get gibberish. If you keep it constant, it's not good, but if you take variation of 5% of the, let's say we have a Gaussian distribution and stuff like that, you start having real distribution of these cracks, which is 13 to 19, which was really perfect with respect to experimental to 14 to 19. So basically, this is really the idea that I wanted to explain in this lecture. We were able to introduce the results that are capable of dealing with material instability. That means complete failure process to go into softening and then final fracture. We said that the best choice of material parameter in our model is the fracture energy. This is the one that you need to go all the way to the ultimate stress and go down to zero. And the original feature of the model that we developed was the ability to take into account dissipation from volume, which is fracture process zone, and from surface, which is macro crack, which is not many models that can do that. And then we pushed it into structural models to be more efficient, something like a beam and whatever, with a different type of arrangement. We also had that for the steel with plastic hinges and stuff. So capabilities of this model go way beyond the traditional continuum mechanics models. They can give you crack spacing, opening, crack population, and they can give you all kind of instability. So basically, this is the stuff that I wanted to cover before we take a break. Okay, we are all back. So basically, what I wanted to do now is maybe I should have just commented on the one that we didn't do in detail. What I was presenting a moment ago was all for a reinforced concrete structure. We did very elaborate for steel structure, but we have to understand a bit more about large deformation, large strain, and everything like that. And basically, we were able to say, for example, study the ultimate limit load of important steel structures like Eiffel Tower and things like that by starting with the material scale. We have sigma epsilon defined for material. And then you do a very elaborate 3D model where you have a large deformation, plasticity, you have instability and stuff like that. And you turn this into corresponding beam element. And you can see that you can get the same results, or at least the ultimate load behavior of this type of result. So let me stop with this type of structure point of view. And what I want to do now is sort of a material point of view. In other words, we can go even better into the understanding of this type of behavior. And in particular, in this part of the lecture, I wanted to discuss how will you get the best interpretation of some of these tests which are used for identifying the behavior of your composite materials within elastic behavior. And in the process, you can quantify the size effect, which is basically the observation that the ultimate failure of a very large structure built of the same composite material, like a small specimen, is not necessarily the same. There's something proportional to size. And unfortunately, the bigger the size, the more likely is the structure for break, because you have a critical concentration of these defects, either initial defects or introduced in terms of the course of loading. So our motivation was basically the fact that that we had to do interpretation of this three-point bending test, which is not an easy job to do, because in cohesive type of materials that you cannot put in the testing machine to do simple tension test, defining the tensile strength is certainly very subtle. Namely, what you have here, this is a simple beam with these two supports here, and then you're pushing with the imposed displacement in the middle. And then even sometimes in order to master the thing, you put the notch, so you know the cracks will be occurring there. And you're supposed to be interpreting the tensile failure strength from such a test. So what is the difficulty? Well, first of all, if you think of the beam bending, if you take a moment diagram, it has very large value here. If this is force F and the length L, you know this is FL over 4. And that means that you have the largest compression stress here, the largest tensile stress here. Here, there's not much stress. So the stress field is so-called heterogeneous. In each and every point X, you have a different value of stress. And on top of that, you have a material which is heterogeneous. So you put two heterogeneous fields next to each other. There's really everything you can kind of obtain. So how would you interpret this, how it goes? So from this type of experiments, people obtain their tensile strength, and then the most, let's say, prominent advocate for this type of thing of size effect was Bajan. Honestly, I never understood his explanation. He was talking about size of this type of structure. So basically, he says when you have like a small size, this is more like a failure by continuum mechanics. When you have a large size, this is like what you call it, fracture mechanics. It goes down linearly with size. And then many of these structures of interest to us are somewhere in between. So you have to kind of define which is the one here. So we, at least I had the problem understanding what exactly is the size, because basically if you think of that, you have a beam bending, and you have both bending phenomena and you have a shear, because the shear stress is not zero here. So you might have materials which are very sensitive to the failure in shear. These are something like metallic material, and the material which are sensitive to the tensile failure. So it's not only the size, it's the kind of material that you have that is dominant failure mode. So instead of that, we kind of try to get a better interpretation of that. And that really means that you have to go to the fine scale interpretation of the material behavior, and then you build the test results of this 3-point bending test from this fine scale. More precisely, what I mean is this. First of all, when you go to very fine scale simulation of your material, this is the most classical domain that is heavily developed in France. It's called homogenization. Basically, that simply means that you take your material and you kind of homogenize. That means you are whatever I put it there. It's bothering this stuff. So basically, in this stuff, you're kind of homogenizing. You can say that you pretend that your composite material is not heterogeneous, doesn't vary the property from one point to another, but you replace it with kind of equivalent value of your properties. So the most successful the result was definitely for elastic properties, and the first work started with computing corresponding Young's modulus for the composite material. So there were like two different approaches in mathematics. This was called asymptotic development, where they take the different scale of, let's say, observation of the material properties, the very fine scale, and then they take some kind of characteristic, let's say, parameter epsilon, and develop the displacement field in terms of the powers of epsilon. So you have a constant value and then linear and epsilon, quadratic and epsilon stuff, without really explaining how you define your epsilon. And then you do this development, which amounts to solving a number of these problems that pertain to different power of epsilon. And then the process you develop your, let's say, homogenized elastic modulus. In mechanics, you have a different story. You have basically story of the structure. This is a characteristic state of the structure. That could be something like 100 meters for your cooling tower. And then if you go down to cement, you have a micron, this is 10 to the minus 6 of a typical type of observation for cement. So you can then place somewhere in between something called representative volume element, which will be a piece of your material where there's enough of these things that you're trying to represent. So in this case, you're actually taking a single point at the structural scale and you're blowing it up to the micro scale. So at the single point at the structural scale, you have one displacement, you have one stress, and you can then, when you blow it up to the micro scale, you can say that the average stress at the micro scale, where you have many now, because you see the heterogeneous structure, should be equal to the stress, which is equal to the macro scale, or you can impose that the average strain, which is computed from this displacement, is basically the same as this macro scale. So it kind of two bounds, up and lower, and we come back to the moment. And basically, if you really want this homogenization to apply, the separation of scales, what is called, should apply. In other words, if a respectable metal structure is something like 1 centimeter, that means like 10 to the minus 2 meters, and then you have a dislocation happens at level micron 10 to the minus 6, then in between 10 to the minus 2 and 10 to the minus 6, you can squeeze something to be a representative volume element. It has enough of this dislocation, so you can characterize behavior of your metallic material. Now, for some of these situations, it might be difficult because typical type of specimen that you use in this 3-point bending test is 40 centimeters long, 10 centimeters wide and 10 centimeters thick. And if you have aggregate, which is like 2 centimeters, you will have 5 grains to the thickness. So there's no way that you can say that I can squeeze my aggregate inside this, unless you want to be testing a structure which is in the order of meters, in which case you can kind of squeeze something called representative volume element. And so you have something, the problem which is representative volume element is not well defined, and this is another difficulty of homogenizing the materials of this kind. So there's something called apparent properties that late Christian was able to define, which is like a substitute for homogenization, but not in the sense that that basically you go to fracture just because you're computing so-called apparent elastic properties. So we're interested not to stop only at the elastic property, we want to go all the way to fracture and failure. So you start by observing your microstructure. That means you have to have access to the details of a microstructure. So you can do this with an electronic scanning microscope, or you can do nowadays a digital image correlation. That is, you glue kind of film on top of your composite structure. And when you deform the structure, also this film deforms, and you can process the displacement field. If the specimen is sufficiently small, you can put it in an X-ray machine, and you can have a digital image correlation where you can observe how the different phases of your material at a very fine scale are behaving and deforming. So then, as I said, when you have this microstructure observation, you want to get the corresponding properties at the core scale, where you call it structure, when you kind of keep it constant. So as I said, there's the most prominent references are the books of Lyons and the book of Sanchez Palencia in the late 80s. Basically, they were done for the asymptotic homogenization. We developed the power series representation of the displacement field, and you solve the separate problems for different powers of this parameter epsilon without ever explaining what epsilon is. And then basically the other one coming from the mean field theory, the works of Zawi, Suki, and so forth, which says that at the material point, you have a single value of displacement, stress, and strain. At the fine scale of the representative volume element, you have some kind of a, let's say that the heterogeneity of the material, and then you impose either the displacement, that is like the stiffest type of structure you can have, or you impose the stress on the boundary to solve this boundary problem for the representative volume element, and you get equivalent properties. Although they never really explained what exactly how you get this representative volume element, what that is. It should be really statistical type of thing, but that's done in terms of the dimension rather than statistics. So basically, we discuss this in the level of concrete because this is the goal of being able to get the better interpretation for this 3-point bending test for concrete elements. So basically, we are now at the scale. We can clearly distinguish between aggregate, cement paste, interface position zone, and so on and so forth. In other words, again, we're going to be running the multi-scale analysis with different inelastic phenomena taking place. And we're going to be using operator split, solving one after another all these phenomena that can, these variables that can do evolution, either the state variable for the global or internal variable locally. Then also, this is done for plasticity. Recall again, when you have the total set of equation, here's the set of equilibrium equation in the rate form, evolution equation for plastic strain, evolution equation for hardening variable. You can run the first part of computation by fixing the internal variable and then computing the evolution of the total strain. And then you fix the total strain and you compute the evolution of the plastic strains and hardening variables. So this is global computation, this is local computation. And the goal of this computation is to deliver a plastically admissible stress field, which will make the yield function either negative or zero. Another thing, again, is that internal variables should take evolution which is much faster than the state variables. So if you're having fracture occurs very quickly, to say instantaneously, also yielding and so on and so forth. So in the spirit of viscoplasticity, that means this, let's say the relaxation type should be much faster than what you have in terms of increasing the stresses. Again, these are the type of frameworks that we assume to be valid in order to have all these approaches making sense. But other than running the classical plasticity and damage, this time around, our goal is to get a better interpretation of what is going on in 3-point bending test. So the idea goes as follows. we take one approach will be standard finite element computation, where you build a finite element mesh, and inside every of these elements, you're building the internal force as a B transpose, B being the strain displacement matrix. This is a typical the derivative shape function with respect to X or Y for 2D case, multiplied by the stress that you compute given the total strain or total displacement, plastic strain, and hardening variable. And then basically, you can go to dynamics, between this dynamic inertial effects or whatnot. And then in each and every point, Gauss point integration, you're computing your plastic strain hardening variable and you're getting interpretation. Now, the problem is if you really want to take into account the heterogeneity of the element, this is pictured here. Imagine now with the aggregate as opposed to cement paste. Let's say aggregate is white, cement paste is kind of here grayish. You take a structured mesh, that means the elements are regular. And basically, because your shape of your domain is regular, so why make it complicated, make it simple? You can find yourself with the element which is crossed by the interface between cement and aggregate. And there's no way you can be presenting this correctly, given that basically you have the heterogeneous strain field that would imply that you have stresses that are the same on both sides. But if the stresses are same on both sides of the interface because of the equilibrium action-reaction principle, the strains cannot be because here's one property for aggregate, the other for cement, and they are not the same. So simply, for example, if you want the epsilon to be a sigma divided by E, one is here, another is there. So these two epsilons are not the same if they share the same sigma. So obviously your interpolation with finite elements which have a smooth displacement will not be correct, and you will have error. So people realize that and say, okay, it doesn't really matter, I'll just go for that. And I increase the number of integration of points instead of 2 by 2, which is enough for 4-node element. I put 5 by 5. And the argument was that this way I can sample, I can find many more points inside the domain, and hopefully they will average in a correct way, but they don't. Simply because you don't really represent the strain field, so you can average as much as you want. Average the results which are wrong. You can have finally the average result which is wrong again. So basically, the idea there is like this is the type of computation we suggested as a computation that, but this is more like I can skip this one. There's like a global computation, then there's a local computation for each element, and the computation there. This is just one of these papers we wrote with Christoph Cassiotis to show that you can go to the stable scheme when you have this operator split with different type of, when you have the operator split with different type of things that you get stability. It's a little bit more, let's say, crazy plasticity where the plastic strain is represented in more and more refined way, as opposed to simply plastic deformation, we then go for heterogeneity and whatnot. And in fact, this is fine as long as certain conditions are met. And basically, you have the contractivity of this computation stuff. This is the result. If you're interested in this type of thing, we have a paper from 2010, and you can do that. But the key thing is how we actually compute it. So we take a macro scale, which is our concrete specimen, 40 times 10 times 10. In 2D, just 40 times 10. And we take here for illustration 8 nodes. And with each 8 elements, sorry, each one of these elements is with 4 nodes. And then inside each of these elements, we put a real microstructure. So you have like this aggregate and you have cement and so on and so forth. You have voids and things like that. So then we introduce the variables, which goes as follows. We have a macro scale displacement, which is displacement of these black nodes at the structural level. Then you have micro scale displacement that are not even pictured here. They are displacing all these tiny nodes. So the mesh is sufficiently defined so you can really, in a credible way, represent your microstructure. And then we have internal variables which are really saying what is going on with the particular damage and plasticity at the level of this fine scale. So instead of homogenization, we are going for 2-scale computation that are taking place simultaneously. And so in this 2-scale computation, the level of element taking into account heterogeneity will be replacing the typical computation of the plasticity. So I won't be computing something like this, where you have a evolutional plastic strain or hardening variable that is homogenized. I'm going to take into account the real heterogeneity of the material and really do computation for real material and fine scales, so I can do this interpretation much better. So my variables to start with are macro displacement that used to be already in the standard finite element model, giving macro strain. And then instead of this let's say, average plastic deformation and so on and so forth. Now I have a micro displacement and corresponding, let's say, hardening variable in this fine scale. So this is the energy that goes in the macro scale. This is the energy that goes into micro scale. And basically, this is the interface. This is the one connecting macro and micro scale in certain manner, just like homogenization is doing, either with the upper bound or lower bound. Maybe I didn't emphasize enough. When you have this imposed displacement for the macro scale or imposed strain to be average for the micro scale, you get the most stiff response. And when you impose the average stress, you get the softest response. So you have these two bounds, toughest, and somewhere in between is really your true behavior. So it's very similar here. I can have like either imposing the displacement, I can have this imposing the traction. This is, you'll see this lambda is playing this role of the traction. And I can have the stuff with the, or stiffest response as we go along. And then I have like external loading and stuff like that. So then I can make some simplifying assumption. We are talking about 3-point bending tests. So I can put external load only to act at the macro level. In other words, it is my traction, which is putting in the middle of the beam. And the weight of the concrete, which is always there, I can homogenize. Doesn't really matter this level. So all the external load is applied at the macro scale. And then at the fine scale, I have to define the energy potential in terms of the micro strain and the micro, let's say, variable, internal variable that I have to use to quantify the behavior of this material. And basically, I have to have a corresponding evolution equation that comes to explaining what exactly is the internal damage into this material with taking into account heterogeneities. And finally, the important thing, replacing homogenization, the scale coupling, which says that the macro displacement and the micro displacement should be doing equivalent work respect to this Lagrange multiplier, which is corresponding forces. So the two works at two scales are the same, just like the basically homogenization will teach you. Only this turns into computational process, which is not done once for all. This is done as long as we do with the plastic developments, we can go change from one regime to another and compute what is going on. So this coupling could be either displacement based or could be stress based. This is equivalent to the displacement base is like this upper bound, Voigt bound, or stress base is Royce bound, the lower bound of your material. It could also be dissipation based. We tried this with Delphi, that actually is the best one in between. So this amounts to this asymptotic equivalent or having periodic boundary condition, making this homogenization to be equivalent with representative volume element, and periodic boundary condition becomes equivalent to the asymptotic element. So it's kind of interesting, both of these groups, group of Leon in mathematics and group of German in mechanics, were working on the same homogenization problem. They suggested two different methods. One is being asymptotic development for Leons, another being up and lower boundary representative volume element for German, and for the elastic properties, they come up to the same result if you have periodic boundary conditions. But as far as I know, they never talk to each other. They just develop separately. So when we did this, we did collaboration with mathematicians, and I showed that with a little bit of probability computation comes from them. So with such a choice of the fields, we can now go for the variational formulation. You have macro displacement, micro displacement, and the Lagrange multiplier merging these two scales into one. So you can take the variation of all these fields with the microfield displacement, macrofield displacement, and the Lagrange multiplier variation. So you get a set of the equilibrium equation, the macro scale, set the equilibrium equation, and the micro scale. What is set equilibrium equation? Basically, this is the computation that takes place inside a particular macro scale element. So this is really fantastic because basically it's very easy to parallelize, because typically in the finite element setting, you're computing the element properties independently. So basically you have a code which is computing the properties of your element inside this computation, and the end result of that will be internal force and tangent stiffness of this macro scale element. Then you go into assembly. What that does, this is replacing this type of thing where you do assembly of this element contribution, so you can no longer integrate over the macro scale element. Macro scale element is only like an empty shell, which really doesn't have itself the definition of stress, but you actually feed directly the internal force and the tangent stiffness that comes from the solving a boundary problem on this level of one macro element. So this boundary problem could be the imposed displacement, which is equivalent to the upper, let's say, limit, Voigt limit, or it could be imposed stress, which is equivalent to the lower limit or Royce limit of this thing. So this is roughly what is going on. So basically, if you have, for example, displacement-based connection between macro and micro scale, what we do is follows. This is your single macro element, a 4-node element, which is, I said, empty shell. It's just used to put inside a mesh of these smaller, what we call microscale finite elements. So here, for illustration, we keep it simple, that these microscale elements are also 4-node elements, only smaller. So being smaller, you can take a better representation of heterogeneity. Each one can have a different Young module, something like that. And basically, then you have to have an interpolation of your microscale displacement. So these are your usual bilinear shape function for 4-node element. Of the macroscale displacement, these are, again, your usual bilinear shape function for macroscale. The only difference here, you have like a local frame, which is microscale, and here you have a global frame, which is macroscale. And then you have this Lagrange multiplier, which is represented with the corresponding shape functions, NA lambda times the parameters of this Lagrange multiplier. So what goes up to the macro scale, when you compute this type of level, are only the macro scale displacement. These are displacement of these black nodes, and the corresponding parameters for Lagrange multipliers, which happen to be nothing but that components of internal force for this particular vector. And of course, you'll need the tangent stiffness, which also you obtain in this process. So in the displacement-based coupling, first of all, I just want to comment, looking into papers from people I know well, with whom I collaborated, as Casey Park and Carlos Filipa. There were people who spent many years working for Lockheed Palo Alto. This is the government agency producing these fighter planes. And then at some point, they got tired. They became professors in Colorado Boulder. And then aerospace, and then they did lots of these papers in fluid structure interaction. So they introduced notion of something called localized Lagrange multiplier. That is, you kind of split the fluids and structure by introducing intermediate surface. And then fluid is attached to the surface, and fluid and solid is also structures attached to the surface. And then we say you can scale this local Lagrange multiplier. So this is precisely the same idea, only done with the finite element assembly. In other words, the boundary of the macroscale element is just this intermediate surface. And inside each of these domain of macroscale element, you have a separate computation. And then this computation is attached to the structural level by these parameters of Lagrange multipliers beta. And so basically, at the structural level, you make an equilibrium equation by doing finite element assembly. So all these beta are stabilizing a structure node. And so this way you can have really like you can scale the beta coming from one part to the other, because when it starts failing, then you want to keep the conditioning of the system in a good way. This is just a type of remark when you do computation, then you appreciate that. If you don't, maybe it's a kind of wasted, but anyway, I wanted to say this nonetheless. So finite element assembly recovers the localized Lagrange multipliers automatically. So if we want to do this displacement-based coupling, what we do is as follows. If you have 4-node element, you take any boundary of this element, given that you have new displacement component D1 and D2, the interpolation has to be linear. So all the nodes which are at the microscale, these white nodes, they have to follow this linear distribution of the macroscale displacement. So this could be expressed as basically like saying that the microscale at certain point of these nodes which are on the boundary should be equal to the value of the shape function of the macroscale element with this particular point multiplied by the node values of macroscale displacement. So this could be set into some kind of fixed matrix, transformation matrix T, which is connecting the displacement of the nodes at the boundary at the microscale and the corner nodes at the macroscale. So this is equivalent to the upper bound or weight bound of displacement-based coupling. You can also do, we are interested in the bending type of phenomena. You can do now stress coupling. So it is well known that among all different elements with 4 nodes, the optimal element when it comes to bending is so-called stress-based element, hybrid stress of Pia and Sumihara. Pia was a professor at MIT, Sumihara was a PhD student. So basically what they've done, that you had like a pure bending of this, what you call it, a 4-node element. So you can know that sigma x in pure bending should be a linear function of y coordinate, and then in sigma yy should be linear function of x coordinate if you change the coordinate system there. And then for pure bending, shear should be constant. So you can build this hybrid stress formulation. We talked about that last time, We have sigma and u independent variables. We talked about that the last model that I presented you for the beam. We can have a stress interpolation, you have a displacement interpolation, and I gave you one homework of this kind. And basically, you can have the optimal interpolation for the stresses. Now, this is your interpolation for the stresses, what I call here lambda xx, lambda yy, or lambda xy. You put this into the matrix, and then you project this interpolation, particular edges of this element, where you have unit vector exterior normal, so you have a sigma times n to be corresponding traction, and you obtain the corresponding interpolation of these Lagrange multipliers. So they give you optimal interpretation of your stress field with the best bending performance. We also tried that. And then you can have dissipation-based coupling. I won't dwell on that too much, but in any case, when I've done interface, I took care of this condition by choosing one of these options. And then basically I'm stuck with the macro scale computation for which I have these internal forces and tangent stiffnesses. So I can get always a new iterative guess for the displacement for macro scale. Then I go into the computation of one element as opposed to another, providing the initial guess for microscale displacement and stresses and so on and so forth. And I'm computing this development, what goes on inside. And this is the kind of thing that you get to solve. There's one big set of equation that is related to all macroscale modes. And then inside each and every of these elements, there's another set of equation where you have for the goal to get this corresponding parameters for Lagrange multiplier, which are feeding into the internal forces of your element. Of course, inside you also have the corresponding computation of the inelastic behavior, the internal variables and whatnot. Of course, scale coupling goes along with the one that you choose, either displacement-based or stress-based. So this is the type of computation you can run in parallel. We have implemented that in collaboration at the time with Rainer Niekamp, who was in the group of Hermann Matisse, with Bob Taylor, who is the author of this code FEEP. So we did a two-scale FEEP development. We have a macro-scale FEEP and micro-scale FEEP. So basically start running by sending to different codes execution of the boundary problem, which is related to a single macro-scale element. You finish this computation, you end up providing the residual that goes to the macro scale, and the tangent stiffness goes to the macro scale. You assemble, you solve for the new iterative guess of the total displacement field in the macro scale, and then you go again to the computation from one to another. So this is really perfect for the parallelization, and we were able to parallelize this and get a very good performance, because basically it's easy if you have a parallel processor with many of these CPU units that are active. Basically, you can put one macro scale element to be processed and the other one waiting. And as soon as the first one is done, you push the second one and so on. So you can keep the load balancing of all these units quite steady and have a perfect performance of this parallel type of computing. Then what you can get, if you have a really like Newton's type of method, you can get perfect performance on both macro and micro scale. Typically, Newton's method will allow you to double the number of decimal point when you get close to zero. So here you have 10 to the minus 7, 10 to the minus 22. It's even better. It should have been 10 to the minus 21. Here we have like a 0 minus, what is this, 6 and 17. So it's like a little bit less. It could have been 18 and what's not. So it's very close to the optimal performance. So you can test it. We also tested at that time, Adnan Ibrahimbegovic was my first student. He's a very lovable guy. He was one of the favorite friends to many of NMT students. But then at the time, we did not have a parallel processing. So when I came back from Braunschweig, where they had a nice parallel machine, because Matis at the time was the head of the computer center, so it's really the most powerful machine to run this. Damian got himself stuck with a network of these workstations that people are using to run their own stuff and then exchange emails. So I told him, for psychological purposes, just take 1 million degrees of freedom, take 10 of these machines, and then connect them. So it took 5 hours. It was not meant to that. And then after lunch, you log in, you see Damian. He became really hated by everybody. No, I'm joking. But in any case, what we could test is basically when you start reducing the what you call it ratio between, or increasing the ratio between two scales, you start getting up and lower bound nicely going to the same bound. You have a scale separation. You can get all these type of theoretical results correctly. We could also test that if you have a demanding problem with a softening type of phenomena, this is illustrated here. Imagine you have two macro elements, and then the failure start in one of them. So what happens initially, you had like corresponding values of the left and right Young's modules to be the same, but then you go into softening, then they become much larger than the other one because this one goes into the kind of very small value. So as long as when they are comparable in terms of stiffness, macroscale elements, you need any iterative method. Here's in Newton's, or this is brought in BLGS, I forgot what the other guys are, Flatty, and Shan or something like that. This is quasi-Newton type of model. I have it described in the book in chapter 2. Then you have Gauss-Seidel. This is simply taking one part and then immediately filling into the bottom part. The Jacobi is the simple thing, take a diagonal part and put all the other side on the other side. So all these iterative methods, when the stiffnesses of two adjacent macroscale elements are comparable, converge. Some of them need less iteration, of course, because a small number of iteration, because Newton is by far the most, the fastest in the sense of number of iteration, not necessarily the fastest in terms of time, because quasi-Newton become better. But then you have no choice if you have really large difference in stiffness, because then Gauss-Seidel and Jacobi do not even converge. That becomes very tricky to solve this problem, and Newton needs more iteration, and BFG needs even more. But luckily, these are cheaper because these are like rank update or rank 2 update of your previous stiffness. You can actually get it a little bit faster. So we tried all these different things and really kind of confirmed and get the kind of that this method can recover whatever you know from the homogenization story and the computation story, and then get all the new story. So what is all the new story? Well, first of all, we said that what was done before was not good. Now the key thing is like how credible you are representing microstructure, because the better you can represent your microstructure, the more credible and predictive results that you provide will be. So ideal thing, you take a microstructure and you take so-called exact mesh, where you really follow this is illustration. We have one void in the middle, so you can adapt your mesh to this void. But then it is really costly because representing details of microstructure of complex composite material, it's really a big job. A colleague of mine, Zoe Rabura, is doing that in collaboration with another colleague, Arasanu. I saw the presentation we're doing. They have these voxels and pixels and whatever, and 3D meshes, and just getting homogenization story to do. It has lots of computer code development. A couple of years ago, well, more than a couple of years, I think it was 6-7 years ago, we did a meeting between US Air Force experts and here in Compiègne that we organized, and basically we brought those guys and they were presenting, and it's just a big effort to get a linear type illustration. So what people are doing, they have done structured mesh. That means even if you have like a interface between those two material, you kind of don't care about that, and you take a mesh to be regular. And so they increase the number of points. So we are playing with this idea, what is coming from work of Zodi and Rigas, where they took like a two-phase material, one plasticity, one damage, filling in the hole with the damage. And then basically the interface between for one particular element, which is cut by interface, you have this. So the increased number of Gauss points to 5 by 5 instead of 2 by 2, because it said you have more of this sampling of the results for this particular element. But what happened here, instead of with the exact result, you have a really failure in the plastic matrix, and typical failure pattern are these shear bands at 45 degrees. What happened when you have this integration point filtering, you have something that turns this failure into the mode 1, and you completely miss the mode, and you miss also the response. These are different values for computed response. You see there's none of them really missing. So we said with Damian how we can improve that, and we did this with incompatible mode method. So this is yet another choice in incompatible modes. When you have a discontinuity of a strain field, you'll see that in a moment. So if integration filtering is all the way up and the smeared model is all the way down, incompatible method is very close to the exact solution. So what is incompatible mode? We come back to this 4-node element, and we come back to the core difficulty that it has to face. Namely, if these are two phases, with Young's modulus phase 1, Young's modulus phase 2, you say by equilibrium, the traction on the positive side of n and traction on the negative side of n should be matching. Traction is equal to stress tensor sigma times n. And then you can develop inside the two components. This is sigma nn, and sigma nis, and sigma nm, sigma nis Monaco. Sigma n is axial stress, and sigma nm is a shear stress. So if the traction is the same on both sides of this discontinuity, you of the material, you have to have these two stresses to be the same. Yet if the Young's modulus and shear modulus are not the same, you can say then the epsilon nn cannot be the same epsilon nn minus, and epsilon nm plus cannot be the same as epsilon nn minus. They have to be different simply because materials are different. Obviously, you don't have that in the standard finite element manipulation of the four-node element. So what you do, you enhance this with another type of incompatible mode, which is giving you a possibility to include the mode n tensor n, which is giving you enhancement for this type of strain component, and m times n, the tensor product, the symmetric part, which is giving you enhancement for this type of strain component, with two incompatible mode parameters, which are called alpha and beta. So again, you can take incompatible mode method to be able to handle all this and to get you really the exact result for this particular case. And as I said, giving you very close to the exact solution. So how do you actually build that? Well, this is your displacement gradient when you have this jump in the strain field that you want to write this way. And this leads to these two incompatible mode method that you have a standard interpolation by the finite elements with the four-node shape functions. And then you have this one alpha times n hat, where n hat is given here, and beta times m hat, where m hat is given here. And then you take derivative, you get your enhancement for the strain field. See, when you are left on the discontinuity, you have one part, and when you're right on discontinuity, you have another part. The same thing goes here for the shear deformation. If you want to impose the patch test condition, of course, you have to make sure that this enhanced strain sums up over the element to be equal to 0. And that gives you this theta to be equal to omega minus over the omega total, where omega minus is the part of the element which is to the left of yours. And this will give you the interpolation, which again recovers very nicely the behavior and keeping the structured mesh. And that was the goal. So this was representing just the heterogeneity and going into, let's say, elasticity or plasticity and whatnot. And now we want to go into more serious type of issues like the size effect. So now instead of taking hypothetical microstructures with a very simple illustration with the same finite element and stuff like that, we have to be more credible in representing indeed the true microstructure of our material with the ability to include hardening, softening, failure, and whatnot. So basically, the idea is that let me just check something if I'm okay, good. So basically, the idea is that I'm going to take this to be, let's say again, the typical microstructure of concrete. So what we're doing with the Arnaud de Laplace, we took a Voronoi cell representation of this concrete. Basically, what are Voronoi cells? You start by taking a so-called Delaunay triangulation. You start by putting the points at a certain prominent places of a microstructure, and then you connect these points one to another. So this actually is worthy goal because let me just maybe explain that in a second a little bit better. So I have this one. So the idea is that I can have a, let's say this is the type of representative element I want to represent. So basically I start by observing the certain number of these points and saying that this is like either cement, this is either aggregate, and so on and so forth. And then I make a Delaunay triangulation by connecting these points with triangles, okay? Like that, like that, like that, and so on and so forth, up, top, and top, and top. This will be typical. And then you take each and every of these connections, so these are the centers of your stuff. You can take it in half, take it in half, and you take it in half. This is LO2, and this is LO2, and then basically up, you start seeing the polygons that are by definition the closest, produced from straight lines which are closest distance to a given point, which is called the center of polygon. So these triangles are so-called Delaunay triangulation, and these polygons are so-called Voronoi polygons. So at sight, they look quite adapted to a microstructure. So you can have a typical aggregates of this size, and then cement around and stuff like that. So we took this to start with to represent a better, rather than having a finite element with structured mesh inside, we were able to build this Voronoi representation of our, let's say, concrete as two-phase material with aggregated cement. And then these two Voronoi cells that next to each other are kept together with a cohesive link. So this cohesive link was, in our case, something like a Reisner beam. This is a geometrically nonlinear version of Timoshenko beam. We'll talk about that next week. We have large rotation stuff because we also use this for studying the failure of this, what you call it, attack of the plane and stuff like that. And then we took a very simple plasticity criteria, which says if the two centers separate beyond certain limit, there's a failure. That means epsilon ij larger than epsilon critical, then you have failure. And also because these are beams, you have a Timoshenko beam, you can have like a cross section. Rotation would be psi1, psi I minus psi j compared against the critical value over the certain limit, then again breaks. And then to take a heterogeneity, what we said, these parameters, epsilon critical and psi critical, are not deterministic, but they are random. They are random variable which has certain distribution. We took a simple Gaussian distribution, and this way, this gives us a better description of this heterogeneity. That really led to very realistic type of response. And when we represented this in one of these days, where you bring industry partners, the guy who was a scientific director of Lafarge company, is one of the biggest companies for cement. He liked the results so much that he gave a job to Arnaud Delplace. So I lost Arnaud Delplace as a research guy, and he went to Lafarge probably to get better paid. So anyway, the idea with these cohesive links was this Reisner beam, as opposed to other people using this Euler Bernoulli small strain, small rotation, because we could then handle very large displacement and very large rotation, because locally when you start having failure, then this thing could be really turning a lot. So you need this to be credible. So what really that amounts to, instead of Timoshenko beam, which simply have psi, here you have a cosine and minus sine, you have to have an orthogonal matrix, and then you get your strain field for the corresponding. We'll talk about that when we go about beams. So here are some typical results. You see basically the idea that in 1D testing, you're having this beams being broken. The heterogeneity is always one they can break. It's actually very robust. And then you end up having something like a force displacement diagram, which is very credible of uniaxial breakage. Then also we can have a biaxial attraction. And so these red lines are these beams. And when you stretch it simultaneously two different directions, you can see these beams be broken, and you start having your cracks appearing, and you have a crack opening and spacing as we go along. So it really started to give you like really representation of your structure. We compare this against the anisotropic damage model, the most sophisticated ones at that time. Basically, they were handling one of these benchmark problems was this beam with the continuous beam with this cantilever part, and basically with this loading that was chosen here, F, and here 0.13 F, the crack occurs and then kind of spreads around here. Here, actually, the crack is not so smooth. It's a jagged edge, but it's if you look into the force displacement diagram, it looks much more realistic in this case as opposed to other case. And then this was also used into a large scale type of loading when you have a very large displacement. Basically, the idea is like in dynamics, we studied this case where you have a big airplane crashing into the structures. And just for the illustration, we never managed to do this for the people because they were already happy with the results we already provided. But the idea we can say the risk of there's like a problem whether you can have a so-called spalling phenomena. That is, if you have a static 3-point bending test, it's one thing that you worry about, there's the cracks. But in dynamics, typically what you do, you drop the weight from a certain height. The weight hits the beam at square root of 2 times g h being the height from which you drop, g is gravity. And then you have like a compressive wave propagating down the road. And then comes to the free surface, reflects, it becomes tensile, and the material which is sensitive to tensile failure, then at that point starts breaking. So that is why we needed a large displacement, large rotation beam. If you run this by Dana 3D, which we did for computation, for comparison, what you can obtain, you can just get this red. That means it's all damaged, but you don't know where this material is gone. And then we try to protect some kind of nuclear storage facilities from this mass of concrete that splits from the main structure, so-called spalling concrete, which has too much of a mass and too big a velocity that could be a kind of risk of hitting the stuff and then still provoking the explosion. maybe it's a good just to give you. I love this simulation. It's really the nice type of picture. Let me just run to you. Okay, here. So basically, that was this one here. You can see you can stretch it in two directions and poof. That's at the point just it breaks. Well, you don't see it here because let's see, let me do it like this. Okay, now with toop, it's at the point it breaks. Then you have this one. You can see it becomes very robust because by the fact that these things are random variables, so threshold is not the same for each and every adjacent element. So it's always that sometimes you can get into nonlinear computation. You go left, you go right, you get the same result. But here it's always like one direction is weaker than the other. So you can be very robust in terms of this computation. And this is the one that I like. This is the simulation. When you have this one, poof, you hit it, and then you can have a bunch of these Voronoi cells that you can quantify the mass and velocity, and you can see what is the risk of basically the failure in this particular manner. So let me go back to my version of I have to kill this guy up. Stop share, sorry about that. Again, up. So we are here, and basically I can then really get the computation of this. But this was still qualitatively nice, but quantitatively we're still not there because concrete is not 2D material. It's actually 3D material. Even if you have this simple bending, 3-point bending test with a 40 times 10 times 10, you have to do it in 3D. So what we've done in the next thesis with the Martin Tefeuille, who is now in US waiting for a job at this Bloomberg University in New York City. Basically, the idea was that we do a 3D representation of a concrete. What you see here in green is aggregate. So you can construct this representation of aggregate with this M-power Fuller dipole curve that is typical of a choice of concrete. So know how many big, how many small you have to use in terms of aggregate, but you don't know where they are because you're producing concrete by mixing it. So you do this, mixing this to put it around, and basically every time you run computation, you have to be doing a different mix, and then you can do the statistics on that. So typically, what the only simplification we did, we took aggregate to be spherical to make it more simple. Other than that, we had the big one and small one and mixing it out. So you can see that in terms of homogenization, we can reproduce the stick perfectly. And what was really important, for example, this is the type of typical thing that we had to do. Aggregate is the white part. Cement is violet. And then the interface is this green part here. So you had the links which are completely inside the aggregate. For these links, we said they are called inclusions. They're just elastic, they never break. And then you have links which are in cement, not so interesting. And finally, the most interesting part is you have links which are a little bit in cement, a little bit in aggregate. And we took the properties that are similar to the aggregate, although typically you would have a little bit weaker points because what you have in real life material of this kind, you have a aggregate which is already dry and cement is drying, so there's something called self-desiccation cracks and that weakens the properties of the interface, and you don't know, and then you have to kind of postulate it and so on and so forth. So basically the idea is like for this type of links, we have a little bit in aggregate, a little bit in cement. There were kind of comparison against XFAM and then embedded discontinuity. There were work of later Belichko Dirashek, where they convinced Dirashek that embedded discontinuity is not good enough. So they went for representing it with XFAM. So what is XFAM representation when you have this? Here you have like two different material properties, and then your interface where this thing is breaking. So you take a displacement field constructed by two standard shape functions. And then on top of that, you have this Heaviside function that is introducing the crack at this particular point. And then you put the field description with the D1 times N1 and D2 times N2, with D1, D2 being the displacement at the nodes. And on top of that, you have two global variables which are also sitting in nodes. Here's alpha 1, here's alpha 2. Alpha 1 is multiplied by this shape function, which is product between heavy side and N1. And alpha 2 is this function, which is product between N2 and the heavy side. And so we have like four unknowns, two normal displacement, two this extend displacement that is being used to get this description of the field. And then they compare that against where you have just two displacement, one debate discontinuity. But I said this is not fair comparison, because if you think what is missing, and they, of course they had a better result. I said, but it's not a fair comparison, because what is missing here, I have no way of describing heterogeneous structure of this material. So basically, by adding such a mode, which gives you the displacement like that and gives you a jump in strain, you can, for the constant stress, describe the strain, which is different on two sides of the boundary. This is like the one that we've done for Damian. So I have one incompatible mode, which is giving me enhancement of this total strain for the what you call heterogeneous material. And I have another incompatible mode, which is giving me the opening of the crack for the complete failure. Hence, I have my set of the global equilibrium equation. This is contribution of particular element to this global. I have it to integrate over the first part of the domain with one material, and second part of the domain with the other material with the corresponding values of stresses that are computed in the center of these elements. And then basically I have an extra equation, which is giving me the contribution, how the traction is computing. When you have a discontinuity, it's that the traction should be matching these values of the stress. And finally, I have this contribution that what is the difference in strain in one side and the other. So contrary to explain what these parameters alpha 1 and alpha 2 are global, and I don't know how to split the enhancement of the total strain with respect to the generalized plastic deformation, which is jump here. Here, perfectly, it's clear. I have here a global set of equation giving me all displacement, and then on top of this one, I have enhancement of the total strain field. So these two equations with F internal minus F external plus H2 are solved at the global level of this element, and then I have to compute corresponding evolution of the opening of the crack for each and every of the elements which has this crack, which goes into locally. So this becomes certainly much more, let's say, robust and really clear what you're doing, and you have the same result, if not better, with this one as opposed to embedded discontinuity as opposed to extend. Then we enhance this to the 3D case. So here are different representation. If you have a simple tension test, you cannot do that in reality, but you can do this numerically. So here we took a certain number of these cohesive links. There's 150,000, 300,000, 700,000. That's what you see in static converge. These are representation of the results in the simple tension test. Either you take contours of the displacement. So red is really moving a lot because it's on the side of the crack, and blue is unloading because it's basically after the crack, you don't have much load. And the same thing is represented in terms of the cohesive links which are broken. You can see that they are really following the interface between aggregate and cement paste, because these are the points where they have a stress concentration. And again, there's no way you can represent this interface correctly, but you can represent dissipation, which is the curve underneath this diagram. Then we tried the same simple tension test for different situation. We have imposed let's say forces in direction X and then Y and Z, and every time you get more or less the same result. So saying that the concrete is statistically close to isotropic material. Then if you want to have a tearing apart the specimen, you have a triaxial tension test. You can see that basically the resistance is larger because you're really taking all these cohesive links at the same time. But the ductility is smaller because there's no reserve links that can help you. In 1D case, you can have some links which are inclined, so they enter into the game later, and that they contribute to this dissipation as you go along. In 3D, poof, you just tear it apart, you get the highest resistance, but the smallest dissipation. Now, with this simple cohesive links represented with initially we did with the truss, we have done it, if you now squeeze it, again, cohesive links start breaking in the lateral direction, and you have a bigger resistance, but it was not good enough when you simply take it to be a truss, because you only had mode 1, and the ratio between compression and tensile test was only 4. And basically, we could still reproduce, for example, something like biaxial compression, that the resistance goes in a little bit higher than the uniaxial compression. And you can see here, by putting more of this aggregate in the tensile failure, there's no difference because you just need one surface. And as long as you have enough cement, you always find the surface. So no matter how many aggregate grains you put, it's always the same. But in compression, the more aggregate you put, you have a higher resistance. So you can kind of build the compressive failure a little bit better. But you can also see that the combination of something like a Drucker-Prager and something like Rankine for tensile, which was used historically by the concrete people, was credible. The only thing you can improve the representation of the compressive failure. Then we said, okay, you're missing the mode 2 and 3. So instead of cohesive links being a simple chassis, which was in one thesis, then we did the next one with the DNA culture when we did the Timoshenko beam. So you could get mode 1, mode 2, mode 3. And then you build the resistance, which is 10 times larger than the tensile part. And basically you have these different failure criteria in mode 1, mode 2, and mode 3. And then you have to kind of feed into this resistance. We use this for different studies. For example, we had if you have a testing on a specimen, not only on this cube, but on like a cylinder. This is used not only for concrete, but also for rocks. Sometimes by taking these cylinders, you damage it. So it turns out if you damage it in the way where it's inclined, it's no big deal. But if you damage in the way where you have this rugosity, when you don't have a smooth upper surface, you have really big reduction. So basically, this is really observed here. If it's kind of just inclined, there's not much reduction. But if it's a bump or there's a hole, there's big reduction because you're kind of crushing it before than it should. So some of these experimental results should be taken with reserve because your specimen is not perfect. And the result that you obtain is really influenced by the shape of your specimen. So if you go along, one should be careful how to take into that. So at the end, we were able to get really very good representation of the final failure. And at the end, we wanted to see, okay, how now you connect this with the description of heterogeneity. So what are the choices? You can do homogenization, and you can represent it. You're talking about structure which is like a bar. And if you go along this bar, you can do homogenization, and you can say that any parameter you're interested in, could be whatever, elasticity, modulus, it could be yield, stress, and so on and so forth, is simply constant for any value of x. Or you can say that for any value of x, there's certain distribution of this parameter. To illustrate, this is taken as Gaussian. And so basically, you can take this to be, for any x, the same distribution. This is then considered to be parameters like random variable, which we did in the work with Adnan Ibrahimbegovic. We also took these criteria, epsilon critic and psi critic, to be Gaussian variables with certain standard deviation. And probably the most credible one is representing it with a random field, which means the distribution is changing from one point x to another. And then you have to be able to provide the corresponding distribution for this random field in order to get the best results for your particular structure. So if you want to get homogenization, of course, you take a constant value. If you want to get a little bit better response for the inelastic behavior, you can take random variables. But if you want to get interpretation of something called size effect, you have to take representation which is really given in terms of random field. And then you can compare heterogeneity of your material with respect to this random field. If you take it as a tropic representation, it's something called correlation length, which gives you the, let's say, the quantification of how likely you are to be homogeneous. We'll come back to that in a second. Then with respect to this correlation length, the measure of homogeneity of your material, you can say what is supposed to be the small or big, or what is the failure pattern that might occur. And basically, for many things, it's kind of not complicated to get this correlation length. Let me go along this line. So basically, what we've done is there's a simple transfer test. This is aggregate, which is green, and the cement paste, which is red. So we are doing this with a different realization of putting this aggregate there, and then running different realization to get this corresponding computation. And basically, we were trying to match this with respect to the 1D model, which has a yield stress and then ultimate stress, and get the corresponding distribution of the yield stress and ultimate stress from all these different realizations. So basically, yield stress was the first plasticity of any of these elements, and we kept this matrix to be elastic, perfectly plastic, so then it goes spreading, and then percolation, it means the plastic goes from one end to another, then you call this ultimate stress, and then you restore the computation, not to go into something. So this way we could build representation of the yield stress and ultimate stress in terms of the corresponding random field. which was given as a, let's say, homogeneous representation in terms of what I call correlation length. Basically, it says you have a variance times exponential or minus x minus y compared to correlation length. X and y are two different points in the beam or in this link. V is the variance, and you can say it's likely to be large or small compared against this correlation length. And so basically, we have 1D parameter, which has a fracture process zone and then softening, like the one that I told before the break. And basically, the parameters are no longer deterministic, but they are now random variables, also random field, which is of this type of representation. So what is the illustration there? If you have a short specimen, this is the specimen which is of the length of the same length, which is equal to correlation length. It's very likely that any parameter you're interested in, for example, here yield stress, the values will be very close to each other. If you have 10 times bigger, the values start oscillating, and if you have 100 times bigger, there could be very large discrepancy between one value and another as you go along x and y. So basically, the idea is that when you have this very large specimen, you can have very large oscillation. Obviously, this is going to break first, but what's surprising, not only is going to break first, its contribution to fracture process zone will be very small. In other words, you can now run this computation with such a parameter with the random field, and we do the computation with a small specimen, medium specimen, large specimens. We have like trigrand, very large, grand, large, and petit, small. And you can see that the trigrand is breaking first. This is now the number of these bars that are broken, whatever, with the percentage, whatever, 10%, 30%, and so on and so forth. And there's not only they are actually broken, but if you look into that, with the very large, actually they are breaking faster, and they're approaching this behavior that is very similar to the like a linear fracture mechanics, the fracture process zone being very small. So basically, what we have here, we have this notion of heterogeneity expressed in terms of correlation length for structures to be able to kind of describe the correlation length. For example, imagine the concrete that we study here. You can say that what you did in terms of from Monday to Wednesday, it's a good quality. Thursday is a little bit worse. And then Friday, when people are rushing to go for a weekend, it's kind of the worst. And then you stop the building of concrete during the weekend. You have like you have to carry on Monday. And basically, definitely, this is the weak point. So whatever you can build from Monday to Thursday, it's fine. And after that, it's no longer fine. And you can then, in terms of correlation length, quantify what is the risk of change of the failure pattern for a particular structure. So many people study this risk of failure. They have something called the Weibull distribution with the weakest link. And this is just a little bit one step more, because we have a fracture process zone and we have this localized failure. So the question, which one of these patterns is going to win with a significant contribution. And basically, then you can get a probability-based estimate of the size effect as opposed to this kind of deterministic type of estimate that Bajant was selling. So basically here, what I gave you is another representation of the modeling of the inelastic behavior of particular material, where you go to a hardening phenomena and also softening phenomena all the way to failure. In this particular case, we did like a two-scale representation motivated by the interpretation of this three-point bending test, where you can have like let's say, a fine-scale displacement here presented in terms of cohesive links of Voronoi cells, which happen to be representing quite well the microstructure of your particular material, and then compare this against to let's say other type of classical model. You can definitely get a much better representation of the inelastic behavior. So of course, this requires not only finite element modeling, discrete models and structure mechanics-based modeling, and so on and so forth. But you have to have more ingredients in building a model. But then again, capabilities go well beyond the traditional continuum mechanics. You can get information on something called crack spacing, crack opening, crack propagation, and things like this in a more realistic way than what homogeneous models can ever be able to deliver. So basically, this gives you a new look on what is really done in terms of testing, because really in what we call material testing, and we call like experts on material, in fact, they're always doing structural testing. You can say that the reliable experimental result could be obtained only if you have 100% the same component that you're putting into a structure and you're testing there. If you talk about the airplane wing, you want to put this airplane wing, which is whatever, coming from an A380 airplane, you cannot really put this structure material, or you talk about whatever the protection structure for nuclear reactor, you want to put this in full scale, not in the 1/4 scale. And then you establish your experimental result under the real loading program at your interest, and you can say, okay, my experimental result is really reliable. Even that is not necessarily the case, because if you have very heterogeneous material, then from one heterogeneity to another, you might have a variation of these properties. So people often forget that you're testing the structures and not the material. And when you do this representative volume element representation of your results, you might be making a mistake, especially the one that goes into the direction of neglecting or not capturing the size effect. And basically, the fact that you don't capture the size effect, that means that your failure on the large specimen goes faster than the one on the small specimen, and this could be very dangerous. In terms of finite element computation, the big deal here was that when you represent your finite element, you're no longer only talking about the stresses. So many computer codes, they have something called UMAT, user material model, where they provide you the strain, and then you're supposed to build computation which gives you the stresses. So if you're talking about localized failure, let's say the user math is not enough. You need to enhance your finite element representation with a strain field. You need something like these compatible modes and things like that to be able to capture all these phenomena. So there are many things that we tried and we're trying. There's like 3D parallel computing, multi-physics, probability, optimization, identification, and some of them I can show you a little bit there. But in a sense, it's really very big domain where people can finally do that. You can do, for example, we did also this collaboration with colleagues from Slovenia. You can kind of optimize the microstructure element in getting like some kind of optimization function, which is minimizing this cost function J to be like either, I don't know, shape of this inclusions or something like that, orientation. And on top of that, you have all these nonlinear equation to be solved. So we were doing this in collaboration with these guys from Slovenia. Igor Gresham was doing postdoc with me, and Markovic was participating. And then when we really stopped, and many things that remain to be handled, see, this is the kind of thing that we study this concrete behavior, we have reinforced concrete behavior, so you can have durability of very large structures, not only there, but in many other places, for large airplane, large nuclear power plants, and so large wind turbine blades, 100 meters long, and so on. But if you really want to talk about durability, you have to go to very fine scale. So this was a reminder of what was really for the concrete. Basically, the fine scale of concrete, you have a cement, a hydration type of product given with the simulation codes of NIST. NIST is National Institute of Standard Technology from Washington, D.C. in USA. So typical length here is 100 microns, 100 microns, 100 microns. So you have 10 to the power 6, 1 million of these voxels, and each of the voxels could be different color. This is one of these different phases of cement. And how you actually build the microstructure is when you're pouring water from top, from left, from right, you have always kind of different chain of these chemical reactions, which might lead to different type of microstructure. Then you have these 16 different phases at the scale of microns. And if you want to go to the structure, which is 10 to the plus 3, you have a difference of 10 to the plus 9. And you want to be able to say something about durability of this. Obviously, there's no other way but doing probability from the start, as opposed to, say, statistical mechanics, which was invented and was illustrated in the so-called Ising model. We have only 0 or 1 with the physics guys working on that. At the fine scale, here you have like 16 different phases at the fine scale. And definitely that was quite a complicated problem, where the probability is playing an important role. There's also a thing about how you actually test these properties in a very fine scale. This is the one that I learned when I was visiting in the Technical University in Prague, when Anna Kuchera was doing thesis with me, and Bitnar was the dean, who was a co-advisor of Anna. Jens Zeman was helping. So they showed me how they do the testing of this thing with the composite materials. So if you want to test elastic properties, what you do, you put a series of this, what you call it, needles penetrating the composite material. So the needles have triangular shape, and they are kind of not uniform. So the more they penetrate, the bigger the area. So typical response is like getting harder, not because it hardens, because basically you have a bigger area. and then elastic properties are obtained by unloading. So then you have like some kind of variability of these properties you can never obtain with certainty, and you can go with that. Then we tried also to go into this durability. These are the first steps that we tried, but didn't really lead to that. And then finally, if I want to say, how would you do identification? Typically what people do, they measure force displacement, but they also measure this, let's say, digital image correlations. I said they glue the part. These are results coming from the work of my colleagues in MT for the glass wool type of thing. So there was the biggest equipment, which was most expensive, was this Astra. You can do controlled deformation in 3 different directions. Most of them were in 2 directions. So you have the specimen, which is placed here, and then you're pulling simultaneously 2 different directions. And at a certain point, you have your film, which is glued to the structure, start deforming, and you can then observe the displacement field, and you can post-process this with the software and give you the displacement vector. You can see that at a certain point here, there's like a crack which is occurring. So when we discussed with these guys, I said, why didn't you take my incompatible? But they were always identifying 1 minus d times z, because this was in the spirit of Lemaitre model, so I never really get for that. Too bad. But in any case, the idea is like we tried identification there. So this was the work of Anna Kucherova. So basically identifying something means that you have an experimental result, and then you have the same result provided by the model. And your cost function should be reducing the ratio, the difference between the one that is given by the experiments and the one that is given by the model. So now the unknown value, of course, it has to be done under a hypothesis that the equilibrium equation, all this is imposed. So here you have the result, it's experimental result, and you have your model stuff, but you don't have the parameters. So now you're identifying the parameters. Basically, it's unknown of the problem, so it could be a different model or Young's modulus and so on and so forth. So when we are doing this with Anna, we identify the model of Delphine with this anisotropic damage model, which has a hardening fracture zone and then softening with these 2 failure criteria. And we also use the model of Bajan being a very important professor from Prague. It took a big courage to identify that. So there are different philosophies of how you represent this, let's say, the model type of parameters. You can have a, let's say, either by I don't know, like a different representation of these type of things. But in any case, you want to really, like, you have a, what you call it, representation could be like a design expense, could be factorial, could be a central composite D optimal random selection Latin hypercrude. So this is like really what kind of values you take, what is the model choice, how you can actually represent the field throughout the measurements. You can take radial function, they have the advantage to be always positive, or realization stochastic process, and so on and so forth. So this is by itself sort of like, and then you put the model fitting and trying to get the optimal value of these parameters. So for example, if you have a Delphine model, I said it was like elastic response characterized by 2 parameters, this Young's modulus and Poisson's ratio. Then the hardening modulus is characterized by the limit of elasticity sigma f bar and hardening modulus k bar. And then softening modulus is represented by the ultimate stress sigma f 2 bars and the total energy that you put into that and related to the material beta. So what we done is we took this 3-point bending test with a notch, identifying these 6 parameters. The idea was to get the proper measurements to define our cost function, that is like matching the force displacement and matching measured displacement there. If you're talking about, let's say, a softening part, the most reliable part would be crack opening. You can measure the crack opening and then try to pilot to work on that. And basically, we have split the set of parameters into first elastic and then this, what you call it, hardening, and then finally softening. So then we were running either like a grid type of computation, or there was what Anna came with, there was like what he called a genetic algorithm stuff, which is just like a fancy way of saying that you do this identification for any crazy thing. And you can see that we can get identification of these parameters in quite good way with errors that are quite small. I mean, the main point is the further you get, the parameters for softening, if you take the same tolerance criteria, they will have the largest error. You go already 2-digit. But then if you kind of squeeze a little bit the tolerance criteria to 10 times bigger, then you can already get it back to converge. This is really the idea that this model has a very sound features that it splits 3 different phases, so the elastic, hardening, and softening, and the parameters are very meaningful in terms of physics. And that identification becomes also kind of easy. Another one was today you have this neural network, you have this type of thing that you cannot build these parameters any you want. So there's a very well-known model of Bajant where he took this to be like some kind of a 128 planes on the sphere, or 32 on a circle in 3D or 2 representation. And for every of those planes, he constructed the axial and shear response that goes into hardening and softening. And then mixing of that y 128 to 32, because that corresponds to numerical integration of this sphere or circle. So it becomes really you're kind of not homogenizing, but you are kind of numerically integrating. And then you put these parameters of such a model that is built from 1D springs into some kind of set of parameters which is in here. The only recognizable parameters are Young's modulus and Poisson's ratio, and all the others are completely unrecognizable, K1, K2, whatever it is. And so no surprise when you're identifying this from compression test, you get just about anything. You can see that these are the kind of things that the variability, and maybe the most important result I want to show is this one. We have very large errors, you have like something like a relative error for Young's modulus is small, but then for the others, it could be kind of of the order 200%, 150%, and so on and so forth. So it took really lots of courage to show these results when you had the Bajant and stuff like that. So basically, let me stop there and give you kind of the overview of what we were presenting today. This is really the idea that you can study in a very fine way the complete failure process from the elastic fracture process zone all the way to the softening. And then the notion of fracture mechanics, as many people take as very simplified, this linear fracture mechanics. You can certainly replace it with a very defined modeling where you start from fine scale and we get the proper identification of the damage phenomena, and also the proper interpretation of size effect, which is certainly very important for your thing. So maybe there's enough for today. I'll stop here.